Okay, Yufan, can you start?
Okay, hello everyone. Today we will talk about empirical study of transformers for source code. It was published on the FSE this year, and it has two others. They are all come from Russia, and they are all researchers at High School of Economics. This is a top university in Russia, and their research interest is mostly focused on the deep learning for source code and the models automatical source code analysis. And here is the index of today's presentation. This survey is a bit long, so we have 6 parts. The first one will have a quick review of transformers. And then I will introduce 5 works this paper presents. And then I will introduce 3 tasks. And then I will talk about the experiment and conclusions. Okay, now we first have a review on the recurrent neural network. I have presented that recurrent neural network just focus on sequence information. You have a fixed length sequence input to the recurrent neural network, and all the neuron is the same, and then it will output a same length output. It captures the long-term sequence information in this model architecture. Okay, now we have upgrade the recurrent neural architecture to encoder decoder architecture. Here we can have remember this question because we use a start and a stop sign to show the end, the start of the end of the sequence, so we can have a more flexible length of the output length. And this architecture is popular in the machine learning in the translation task. Okay, now we also talk about the attention. So here I want to emphasize that what we have talked about the attention is the encoder decoder attention. This name means that this attention is between the encoder and decoder. That means it compares the relativeness between the encoder and the decoder. Remember this score is between one hidden state in the target, it is a decoder, and the one hidden state in the source, it is the encoder. So the score function may be quite different, but this is the the most important thing in the encoder decoder attention.
Okay, can you specify the HT and HS in the graph?
Oh, HT is actually
So HT is here, right?
yeah, is the blue one, and the
Okay.
HS is the green one.
So that means given an arbitrary HS here,
Yeah,
it will be, we will calculate
a score. This score represents the relativeness of the two neuron,
two neurons or the set of or a set of neurons
yeah.
here, right? So this means that there's supposed to be a weight to calculate these 4 neurons, giving that this HT, right?
Yeah. It computes the similarity between the each HS.
And here, so will you please specify more about this S prime here? S prime.
S
So
prime is just different from just that means because for a specific HS, and the other hidden state of encoder is HSCP. It's SH dot.
by the way, can HS be one of S prime?
Yeah.
It could be, right? Correct. So anyway, so this function means that given an arbitrary, given HT, and how important it is for or the importance contribution or the relative importance contribution of each neuron to this HT, right? So it is actually using a softmax to do this.
Yeah.
And also there's also supposed to be a temperature there to control, to avoid the gradient disappearance.
Yeah.
Okay. So I think this is quite clear, right? So this part is kind of
Yeah,
clear.
you can
So
just
okay,
repeat
so
it.
we discussed this before. I just raised questions to warm up my memory. So anyone have the questions, you can just feel free to interrupt. We can further illustrate a little bit.
Any question?
Okay, if there's no questions, let's keep going on.
Okay, so now we look at the transformer. Just overall, we can see that this is quite similar to the encoder-decoder architecture. It just inputs the sentence to the encoder, stack with 6 encoder, and then to a decoder also 6 decoder, and finally get a final output. But for the detail, it's quite different. Here is a self-attention. It's quite different from we have talked about the encoder-decoder attention. So today I will first introduce what is the self-attention. Here I just raise a very simple question. The animal didn't cross the street because it was too tight. What this it represent? Anyone, maybe Yufan, could you answer this question?
Animal.
Yeah. So in this question, this word it actually represents animal. So this is actually why we use the self-attention. This self means in this sequence, this word animal have a much importance on the it, under this token it. So maybe, if you want to explain this embedding, it's much better to consider animal, but not other words.
I think another candidate is street, right? So for machine, it may not, even if we have the phrase or the word property, we know the animal is a noun and the street is a noun. But for the machine, for human beings, it's very easy for us to know that animal or anyone is the most likely word it refers. But for the computers or for the machines, it may also consider street as the potential phrase which referred by it. And so here, just Yufan mentioned, and we need a model to emphasizing that the animal is the more likely options which is referred by it.
Yeah, it's just like you give a high weight on the animal word. Maybe other word is just like 0.1 and the animal is 0.8. And then this model will more consider animal when predicting it, when consider the information of it. Okay, this is the reason of the self-attention. So it is the self-attention. It's not like what we have talked the encoder-decoder. It's just in one sequence, in his own sequence, it will have attention. And here we will have a deeper on the self-attention. This is visualization of the self-attention. We can see that in the model, the attention weight is much higher in the animal. So this means this mechanism will, explain something. Okay, now we look at how to compute this attention. First, we now have an input thinking machine. We first have an embedding, maybe like 512 dimension embedding, and then we will get three vectors. The first is queries and the keys and the values. These vectors are computed by WQ. That means you just multiply the X and the W and to get the query keys and values. So it is just trained weighted to get, this is the trained parameters to get the three vectors. And the second step is to compute the similarity score. Just similar what we have talked about the encode-decode attention. Here the score is about the queries and keys. So this idea is just come from the database. When you want to get a value, you first in the database, you first get a key. Oh, you first get a query, sorry, and then you use the query to find the most similar key. And if you find the most similar key, you will get the final value. So it just follows this architecture. Sorry, and you compute. You just multiply these two vector and to get the final score. This is
by the way, so here the final score is irrelevant to value, right? So given you here, so here the value is not haven't played a role here, right?
Yeah. Because it's just to compute the key similarity. Okay. Now the second step is just softmax the two words. That means the thinking and the machine have its corresponding weight. And be careful with it here. The query, now we looking at the thinking word. And so the query is just the Q1 and the key is different. Just remember, just thinking about what I have talked about the database. So you now compute the similarity between the query and key and get a similarity score. You can also say the relativeness score. And then this score means that how much similarity between the thinking and the with his own word thinking and the machine. Okay. Any question here?
I think the questions in this, I think this is very detailed, but this is very useful information. And what Yufan is talking about is actually a very important. I think a lot of us have already tried to know the knowledges. These ideas come from the paper "Attention is All You Need," and I think we mentioned this paper a lot of times in our past discussion. But not all of us are focused on NLP research, so it's better for you to raise any questions if you have puzzling. Okay. If there's no questions, let's keep going on. And also, I think it's good to have questions, raise questions from time to time, not only for the audience, but also for you fan, so that you can have the interactions.
Okay, so now we have the softmax result. You can just regard this as a relativeness score or similarity score, and then you compute, just multiply with the value. So you just get the final embedding. So during this self-attention, you update the embedding of the the thinking with the self-attention mechanism. So I think it's quite easy using this example. I think there are any question here?
Hello, Yufan. Can I ask why is divided by 8 times square root of dk?
Oh, it's because it will make, in the paper, it said it will make the gradient more, steady, because here is 112 and this is much smaller. It's just, model setting. And typically it's just divided by 8 because the dk is the dimension of the query keys values.
Okay.
You can think about it. So basically, you can think about it here. The softmax is based on 14 and 12, right? Yeah. So it will generate the 0.88 and 0.12. You can have a try to using this apply softmax on 112 and 96, and it was supposed to be their softmax value. Maybe this might be 0.999. I don't know. I just make up the number, and it's supposed to 0.0.1. In this case, when we do the backward propagation and the update, there almost will be no update based on this value, right?
Softmax. But here the test is not. No, here the test is not classification. So how do you know the gradient is large or small?
Because it will be zero. Because this is part of the backward propagation, right? So
your backward propagation. What is your ground truth of your backward propagation?
The ground truth will be final output. So this softmax will not be the output layer. It will be an intermediate layer. But the intermediate layer using an active function of softmax here.
Yeah, then how do you know 0.99 and 0.88? Which gradient is larger?
No, because you can see this value is 112, right? This value is 99. So you're supposed to be have E112 plus E96 and over E96. You can using the calculator to see how small it is, right? Think about it, because this is actually much larger. Maybe the value is much smaller than 0.001.
Yeah.
Yeah, and as a result, if we want to backpropagate based on this branch, there will be no gradients from this branch anymore. I think we discussed this problem before, and I think that is question I raised to Yufan, right? Yufan, do you remember?
Yeah, I think once we have discussed it.
Okay, is that clear?
Okay.
Okay, anyway, good question.
Yeah, it will update this weight matrix. So it will if it is divided by 9, divided by 8, this lead to having more stable gradients. Okay. Now I have a quick review on the self-attention. We first have 3 matrix trainable weight matrix to get accurate e-value, and then compute a score and multiply with the value and get final new embedding of the token. This is the self-attention. Okay, now we talk about what is multi-head. Multi-head attention is just quite simple. You just have you just have multiple matrix. You have multiple trainable weight matrix to get multiple, final new embedding. So it's quite simple and just copy the idea of the self-attention. And here is why we need multi-head. So go back to the example we have just talked about. The animal didn't cross the street because it was too tight. In some, some task or some sense, actually it is a tied animal. Could you understand? This is a tied animal. So it's not a typical animal. It actually have some conjunctions to describe this animal. So in some, some attention, different from just we have talked the animal attention. This is a tied attention. So here it will be much higher. So multi-head just means that we have different view of the sequence. Some view we emphasize something, and some other view we emphasize some other things. Okay. Any question here?
Okay, keep going on. Oh, by the way, any question here? Okay, if no questions, let's keep going on.
Yeah, now we have the encoder because.
Oh, by the way, how do we concatenate the different multi-head? So the multi-head we combine them into the.
Yeah, just use another weight matrix.
Oh, I understand. So here, suppose one head will generate Z1, and another head to generate Z2, and Z1 is supposed to be 1n, and this is supposed to be 1n, and the concatenation of Z is actually suppose there is only 2 head, it will be the 2n or 1 2n, maybe 2n, right?
No, it's just similar with X. It's different from the.
I mean that anyway, this Z will be used in the follow-up computation. Yeah. So my question is that how do we concatenate Z? Because each head each head of attention will derive a z vector, right? And how do we combine or concatenate the z derived from generate? Okay.
Yeah, you got the concat
in the on the vertical perspective, right? So it means that suppose we have suppose the multi-headed, suppose m are multi-headed, and the final z will have dimension m n, right?
Yeah.
Okay.
I think it's m times d.
What is d?
D is the hidden dimension of z.
Your d is the n, I mean here.
Z1 is length of the vector times d. And then the final z would
I think z was supposed. I think the shape of z, the shape of zi is actually one times n, right?
No, so it's a matrix. It should be a matrix.
No, it should supposed to be a vector, I think.
I think it's a matrix.
One actually means the number of samples. Let's talk about one samples at a time.
That means you just use the thinking word. There are no.
Yeah.
You mean one word? Yeah. So it's one. Yeah. I think the same because yeah. Okay.
N is what?
N is the dimension of the key or value.
The hidden dimension.
What do you mean by hidden dimension? Maybe you're right. It's just a hidden dimension for a single word.
Yeah.
And so now we come to the question that how do we concatenate or combine if we have multiple heads? Suppose another head generates C2 equals another N1 N, right? And in this case, how do we concatenate them?
Just you said 1 to N.
1 to N. Okay.
Yeah, that's
okay. So in this case, there's 8 head, right? So here, in this case, in your example, there's 8 head.
Yeah, because because originally it have 512 dimension. This is the X dimension, and this is 64. So it needed to have 8 heads to get final the same dimension of X.
Wait. So the embeddings of the word thinking is 512 dimension.
Yeah.
And what is the dimension after we apply?
Curie is 64. The Curie key value are all 64 dimensions.
Okay, I got it. So basically, so we will design a multi-head. So we first split. For example, if we want to 8 heads, so we try to divide it 512 by 8, so that we have 64. So in this case, the Curie dimension was 64, so that we can match the 8 heads. 8 heads. After we apply 8 heads, the hidden Z will still have exactly the same dimension of the original dimension, or the number of original dimension of the embeddings, right? So we keep doing these layers by layers, and so that the dimension will be preserved. The number of dimensions will be preserved.
Yes.
Okay. It's good that we recap the detail. So this technique is actually kind of important, especially if we want to make a breakthrough for a new approach. Okay. So I think it's very clear now, right? Now let's keep going on.
Okay. So now we have an overall of the encoder. I think we all know the feed forward, so I just skip it. Now use the self-attention, we get the new embedding of the Z1, Z2, many Z. And here is my question: can this structure capture sequence information? Maybe Xiangling.
I think yes, because you calculate. Oh, which structure do you mean? The encoder?
The encoder, yeah.
Yeah, I think so, because you have self-attention and you look at your whole sentences.
But
Huh?
because for the you can see the here is a formula. Yeah, that's actually no sequence information between Q and key. Could you the sequence information means that like the first word, the second word, the third word, but actually all the words have the same curious, have the didn't show which position he is in this sequence. Could you understand?
Maybe I can help explain a little bit. For example, the thinking machine, right? And suppose I add several words before, and the calculation will be independent, whatever the number of the words I included before. So based on this calculation, I think that is what Yufan means. So suppose that means we shift the word thinking machine 3 words later, and the calculation, the result of the calculation will still be the same. And I think Yufan means that if we shift the word a little bit, we want the calculation to be different. Or in other words, we want the calculation depend on the position they appear, right? But basically, it's better to say that we have some relative position, because thinking machine, the result of thinking machine could be remain the same. We don't shift it. But sometimes sometimes the position actually matters. So maybe we can listen to Yuchen how to justify or understand the position perspective from the position point of view.
Actually, the position is very, very important. From my experience, if you don't use the sequence information, the performance is quite low, actually, from my experience. Okay, so if we want to add some sequence information, we need position encoding. That means we need to add a position embedding, just contact the position embedding to the original embedding. This paper used this formula to get the position embedding. It's quite, a bit complex, but it has some reason in it. But it's a bit.
At least it's periodical, right? The periodic, right? Because you sign cosine here. So in the rationale and justification, I understand that the periodical it is very important. That means sometimes we need a range to keep the relative positions, but given that seems that you mentioned that it's a bit complicated, and there's also some power functions. Any justification for that?
No, I didn't prepare. There are papers talking about this, but I didn't prepare here because I think it's a bit difficult. Yeah, and today I will present 4 works, and 2 of them just changing the position encoding because this is a bit complex, and he used a bit simple one. So I will talk about the simple one. Okay. And here we can, have a further discussion on position embedding. It's a bit complex, and add and normalize is also, some very complex one. Actually, it is a residue of the residue network. You can refer to this paper. I also didn't, talk about normalize here. And now we look at the encoder and the decoder. Actually, for the decoder, there is some different, because now we have the self-attention. Now we have a different encoder-decoder attention. Remember, we have talked about the encoder-decoder attention. It just used a hidden state from the encoder, HS, and the HT from the hidden state of the decoder to compute a score. But now we have the, the K, key value and the Q rate. So it's different. So maybe here I can ask a question. Which query? So for the decoder, actually, we use decoder as a query because now you can just thinking for every neuron in the decoder, we want to search the most similar word in the encoder. So here we regard the decoder as a query, and we want to find the most similar key in the encoder to get to compute the attention. Here is the picture. You can see that we use the key and the value of the encoder, and now the decoder will have a query. And now we use this query to compute the similarity with key in the encoder, and then get a final score. And this score will multiply with the value in the encoder. So actually, this mechanism is just the same as the encoder decoder attention we talked before, but it's a bit different is the key and the value and the query. Any question here?
I think I need to raise a question here so that everyone can follow your explanation. So the point is, I think let me first rephrase Yufan's explanations based on my understanding. You can correct me if I'm wrong, and also then I'll follow up with my questions. So the first conception is that what Yufan talk about is a generative model. And for the generative model, as I remember that there's a talk given by Xiaoling, actually, there was actually where we have beam search here. But basically, we need to generate the token token by token, right? We first generate token 1, token 2, and then we generate token n one by one. But of course, in some models, they will generate all the tokens at once. So let's talk about a normal case that we generate token 1 first, then generate token 2 first. So here comes the question that how do we generate the first token? And we know that the first token, as Yufan mentioned, that suppose it is a wall, there's a sequence of wall, we basically need to know which tokens or which embeddings in the encoding part is most relevant for the token, for the first token. So basically, we will start a query in the decoding part. So, but here I still question that is how do we derive such a query in the first in front of the very beginning? This query will be an arbitrary query, or where is this query coming from? Or maybe start from the embedding position embeddings or someone else, some other embedding there.
Yeah, mostly just the CLS of the encoder because.
So anyway, so here is a CRS. CRS is a vector derived from the embedding from
encoder,
from the encoding. Sorry, from the encodings, and this CRS actually means contains all information of the input sentence. So they will actually as the input, and we're using this input or CRS to derive an embedding vector. And similarly, we're using these embeddings to combining with key, search or using this query to search for the key and derive the first token, right? If I understand it correctly. So my follow-up question is that how these vectors are used. Because for after we finish the embedding encoding layers, on each position, we have a key and we have a value, right?
Yeah.
And for if we derive it, suppose we have Q1 here, suppose that means K1, Q1, and then let's regard of the normalizations.
Yeah.
And then we
that's the same formula before.
Same formula, and how do we combine with V and have V1? Am I right?
Yeah, I just.
Sorry.
This is the formula.
So this is okay. Yeah. So anyway, this K1 times Q1 then times V1, right? And that will derive another Z, right? Derive another Z. And my point is that because we have maybe we have NK So we still have K2 times Q1 times V1, V2,
Yeah.
V2, right? And we will derive Z2. And how do we combine V1?
No. This is the score. You know, you just add this is the score. This is V1. This is the score. Key multiply Q is the score, and then multiply with the value, and then get a new value. This value is
they were combined together into V1, right?
Yeah.
Okay, yeah.
This is no Z2. They are all combined to Z1. Yeah.
Okay, I got it. Let me recap it a little bit. So yeah, so the calculation is a little bit complicated. So K1 times Ki times Q1 will be a score, and the V is actually be here, and add together into Z1. Okay, that makes sense. Okay.
Yeah. So the difference is that the query is in the decoder, but the key is in the encoder. So it's different. Okay, in the self-attention, they are all come from the same sequence. But for the encoder-decoder attention, they are come from different sequence. Yeah, this idea is actually come from, I just talk about this encoder-decoder attention. They just from the hidden, one is from the encoder HS and one is from the decoder HT to compute attention. So the transformer is actually add a new mechanism, the self-attention. This decoder attention is actually the same.
And how do we calculate Q2?
What?
How do you? So we just talking about how we calculate Q1, right? And the result of Q1 will generate the first token for T1, and T1 is supposed to be used to generate Q2, right?
Yeah.
And how do we generate Q2? Just to convert it, or the input is actually just taking from the T1?
Before get the T1, you will have another, another hidden,
Okay, another Z, right?
Z1 maybe.
Z1, yeah. And then we use Z1 to derive Q, and use the Q to combine with a set of the Ki, Vi to derive another another embedding there. Okay.
So the encoder decoder actually different. Here is actually have some sequence information. You can get it, sequence information, because you use the last word to generate the second word.
Yeah, the Q1 actually using Q0, and Q0 is basically CRS. And once we have Q1, and we use Q1 to derive Q2, and so on and so forth.
But sometimes the decoder, yeah, I don't know actually. I just thinking in the decoder actually use some sequence information, so it is different from the encoder. The encoder didn't use any sequence information. It needed to have the position embedding I just talked about.
That means that we are not using the T1 as the input of Q2. We're just using the position embedding of P2 to derive Q2. Is that what I mean?
Yes, that some transformer would maybe use this architecture.
Yeah, it's very hard to say which one is more effective.
Yeah. Okay.
Yeah, I think you're right, because we just need some embedding to start with or derive a Q, right? And whether this Q is relevant to QI or dependent on Q, whether QI is dependent on QI -1 or dependent on the position PI, it is I think it may be effective from case to case, right?
Yeah. So it remains a question.
Okay, so I think Yufan have explained the principle of transformer quite clearly. And is there any questions on the model?
Hello, can I ask, shouldn't the Q be learned together instead of generating one by one?
I think the transformer to generate a Q will be learned.
But Q is a weight matrix, right?
Yeah, Q is. So do you remember there is a WQ there?
Yeah.
So anyway, so once we got a value, suppose let's using position for simpler. So given a position pi, where we were calculated with QW
to get Q
I, maybe this one, or they're the same, whether they're uniform. So that we can derive QI. Once we get the QIs, we feed into decoder, and it is supposed to be, we're still using the self-attention layer, right? So then we start having embedding VI, right? Or we given the QI, we combine the QI. Once we got the QI, we combine, we derive it into ZI. When we got a ZI, we feed into self-attention. And that is supposed to be the procedure.
Yeah.
ZI is derived from self-attention, right?
No, ZI is derived by the query, combined query key and value.
Yeah, then that is self-attention, right? That is encoder-decoder attention.
It is combined with the decoder attention. Suppose there's the final KI, VI, VI. So then we combine this Q with VI and to calculate with the Z.
Yeah, and also QI should have attention with the previous Q to get the self-attention Z.
You first go through the self-attention and get a Z, and then this Z goes through encode-decode attention. I get another Z. Yeah.
Okay.
The first is the self-attention. The second is the encode-decode attention.
So actually, this line from T1 to Q2 does not exist. This is wrong, right?
Yeah, maybe. I also realized
because Q2 is just from here, so it's not from the output.
Maybe it has some initialization, we don't know.
Wait, Robin, sorry, I missed your point. So suppose this QI plus 1, right? What do you mean? You mean it's come from the QI or coming from the KI plus 1 and the VI plus 1?
I mean, this QI will be compared with Q1 up to QI. So it will not look at the T1 here. It will not look at the previous output.
Oh, yeah. What do you mean? Yeah, right. So this line is incorrect. We just taking from we just looking to embedding the input embedding of the TI.
Yes, here remain a question with how he generates the Q2. Did he use the the output of Q1? Yeah, I just remain a question.
But if you use the output of T1, then because one of the advantage of transformer is it can be parallels. So if you use the output of previous token, then you cannot parallelize.
Yeah, but maybe it's true. Maybe it has some.
But anyway, do you remember there's one called the Bing search, which is introduced by Xiang in last presentation. It's called a Bing search. If I remember correctly, it's how to spell it. So the Bing search need us to generate token by token to decide which token to choose.
Yeah, beam search cannot be parallel because it is computing some joint probability, and this token probabilities depend on the past token probability, so you cannot separate them out.
Yeah, and maybe we can leave this parallelization aside, and let's keep going on. And Yufan, you haven't introducing the encoder-decoder attention, right?
I just introduced it.
You introduced the encoder-decoding attention.
Yeah, I just said. The self-attention is the same in the decoder self-attention is the same in the encoded self-attention.
Oh, your encoder-decoder attention means that we calculate the embedding with regard of KI, VI in the last layer of the encoder, right? So that is called encoder-decoder attention. Okay, okay, keep going. But in this case, once you have the self-attention, so it means that the self-attention is partial self-attention, right?
Yeah.
So suppose if we generate only 3 tokens, and assuming there's 10 tokens, we need to generate it.
Mm.
So on the decoder part, if we apply self-attention, we only apply self-attention on the first 3 tokens.
I think the rest tokens are masked.
Yeah, but if
Yeah.
they're masked, it actually doesn't matter.
Yeah.
Yeah, but you know, in the paper, actually, the decoder has sequence information. That means they use the output of Q1 to get the Q2. So
that is fine. That is fine.
that means it's no parallelize. This is very important,
Huh?
actually, because if maybe I use another picture.
But how do you define parallelization? Because we have maybe
Yeah.
n samples.
Yeah.
These samples can be parallelized as well, right?
That means you first get an I, and the I will input to the decoder and get to like M. I am a student. So that means this is a sequence. So this means there are no parallels if you want to use the previous information. Okay. Yeah, in the paper it uses, so the encoder can be parallelized, but the decoder can't be parallelized. You can also refer to the blog I shared in the WeChat group. It has a, you know, the vivid video and show that it also follows the typical
Oh, okay.
yeah.
Okay, so overall, I think the idea is kind of clear. And by the way, my last question is that the fitness function, the loss function here, is by calculating the beam search to calculate the loss function, right?
Yeah, I also share here. Yeah. It has a softmax to get a vocabulary size vector and get a final result. I think it's not beam search actually.
But how do you define the loss function?
The loss of just the logics here.
Cross entropy, no?
Yeah,
The
yeah.
normal cross entropy.
Yeah, I understand. So
Like the golden label is 0, 1, 0.
but when you try to derive a new sentence, we are still using beam search to generate the final output, right? But during the loss function, and I understand the loss function is actually kind of the cross entropy, a sigma cross entropy, etc. But how do we define the y hat here? Because if we're using beam search, we may derive different y hat.
Yeah, I have said this is like the golden label. You can regard this. This is
I
1.
understand that this golden label, the cross entropy is going to compile y hat and y, right? So this is cross entropy, and the input is y hat is our prediction, and y is golden label.
Yeah.
But whether we apply beam search, we will generate different y hat.
I think here you just look at the most likely generated sequence. But
yeah, the point is that
it's like beam.
for
beam search, you can have it's just you look at more possibilities, but now your y hat is just one possibility.
Yeah, the point is that when we calculate the cross entropy and what kind of y hat we can apply, if we do not use beam search, we just got using the y hat of the
one with the highest.
Yeah, the one with the highest probability there.
Yeah.
And but we're using beam search, we may derive another y hat prime, right?
You just don't look at the top 2. You just look at top 1 y hat.
No, the beam search is like we look into the.
I think beam search is more used in evaluation, not in training.
Yeah.
Maybe we need to confirm that because we will use it in the practice. But when we train a model, we do not use beam search. It seems weird, right? So with or without beam search, we will derive different sequence of y hat, and we will have different kind of loss function or loss value. You can think about it. Maybe we need, because I didn't go through the details, and also maybe my memory is fading. But I suggested that maybe you can look in details whether the evaluation requires beam search during the training.
I think during training there are no beam search. It's just
no beam search. Okay, you are sure?
Yeah, I'm sure actually, because I trained before. There's no beam search.
Now, what if we apply beam search during the training? Since that is my follow-up question.
Then you can have different white hat.
Of course, we have different white hat, and also maybe we have more accurate, because suppose y0 hat will be always the same, right? Whether we're using beam or beam search or not, but maybe not. So, but if we're using y hat 1 or y hat 2, it will be quite different if we use or use not.
Oh, so you mean the first word you generated is always the same because you just take the maximum. But then for the second word,
so for example, if we generate sentence, good morning, right? Good morning or morning good, right? Suppose we are translating some word like 早上好, right? So 早 actually corresponding to morning. It's very clear. So morning will be very high, 0.8, and this is for 0.15. But if we combine sentence good morning or morning good, and the probability of morning good will maybe decrease to 0.5, but it will go into 0.7. They were totally different. So in these ways, whether we need to evaluate or calculate the loss function with or without beam search, I just feel a bit. I'm not sure as well, but I think it is. We need to go through that. It will be more clearer to us.
I think here is like beam search with search size equal to 1. So you only keep the one sequence.
Yeah, so if we keep one search, we will generate some sentence on the morning good, which are very high, very high probability, and our goal is actually to generate good morning, right?
Yeah, and then that will be corrected by the cross entropy loss.
Anyway, this is open questions. Maybe it's too costly. Maybe there's too costly if we apply beam search or whatever, because each time we calculate the samples, we still need to search all the way. It will be too expensive or too costly. That is all understandable. Quite makes sense. But anyway, so I just raised my question here. This might be an open question. If in the paper they actually do not use beam search during training, that is fine. And I believe that there is a justification there. I just raised the question here. Maybe you can keep going on.
Okay. I think I have a basic comment. I think your thinking is just a typical RN because you think the zao means morning. But actually now we use the encoder decoder. So now the first token in the decoder actually not means the first token in the encoder. They're totally different. Okay.
I understand, but even if we're using attention, the morning we're actually corresponding higher than zao. Maybe Shang actually will contribute maybe 0.3, but Zao will contribute 0.7. So Zao actually will still highly correspond to the word morning. But of course, that's just a hypothesis. I'm not saying that's 100% correct. I understand that Zao, Shang, Hao actually they will combine all together. Maybe the Shang will also contribute a little bit to the good, and the probability good will be higher than 0.15. This is your point, right?
Yeah, but actually the first golden label is actually must be the good because in the English, there's no meaning for the morning be the first word. So for the decoder, he don't consider about the encoder. They are totally different. For the typical RN, it will use the zao to predict the first word. But in the encoder decoder architecture, it uses the COS to predict the word as the final morning.
But what about hi 早上好? Let's translate this sentence. Then Zao will actually play a role here, right? Whatever it is, Zao will play a role here. And also giving even if we have CRS, and we still have the key and the KI and VI of Zao in this position.
Yeah.
So it will also make some contribution to the word morning.
Yeah. Yes.
Right.
Yeah.
So anyway, so there's no statistics. It's better for us to have the debate based on the realistic example. But I think you're right that sometimes when we have an embedding, when we have the attention, it makes things more complicated. And Shao and Hao may also can raise the probability of good instead of the morning. But But let's keep this put this discussion aside, and let's keep going on.
Okay. Now this is the overall of the attention of overall of the transformers. Let's have a short review. First, we have the input embedding. You may think it is 512, and then you contact with the position encoding. It is very important, and then it will be a bit complex. And then you first have a self-attention and feed forward and add norm to get the final, the Z. And at the same time, the output will have an output embedding and also a position encoding and have a self-attention here. And then it will have the encoder decoder attention, and the final result will input to the feed forward and the linear and the soft maps to get the final result. I think this is the overall architecture. Any question here? You may just remember this architecture. It's a very, star model in the natural language processing. Okay, so now we have some questions. What is the pros and cons compared with the CN and RN with, transformers? And we can also compare with the sequence to sequence with attention. We just talked the first. We can compare these models. Anyone have some mind? Actually, Yufan have just said, maybe Yufan talk about the pros.
It works in parallel.
Yeah.
You don't need to process in token by token. And compare with CNN, I think it tries to borrow the idea from CNN.
Yes, CNN also parallelized has a kernel. Yeah, but what's the cons of the CNN?
CNN only looks at local region, does not look at the global relationship.
Yeah. So the RN actually very suitable for capturing the dependence of long distance variable length sequence, but actually it is difficult to parallelize. So the transformer just combines these two advantages. It can parallelize in the encoder, and it also captures the long distance information. Okay, so here is a conclusion of this transformer. And any question here?
By the way, so when we are training our own transformer, we do not apply beam search during the training, right?
Yeah.
Okay.
Okay. Any question? Okay. So now we go to today's paper. The first is this paper actually is about empirical study of transformers for the source code. So as this is the typical architecture of transformer, we just use this model on our task and do some small changes on the model. So the first changes is the embedding. We all know that the code is not actually the sequence, is actually a tree, an AST tree. We can represent the code as an AST tree. The second possible change is on the positional encoding, because it is also because it is a tree. It's not a sequence that can have a very easy position encoding. So here I will introduce 4 works. They are all do some difference on the embedding. The first up, we have a short review on the AST tree. If this is the code, LM equals list IDX, and here will be the syntax tree. And I think a very naive thinking that is just a depth first traversal. That means let the tree become a sequence and input to the transformers. So this is our today's first, a very simple way. The first is to traverse AST in some order. For example, in the depth first order, and then make the code become a sequence and input the sequence to the transformers, get a new embedding. And then it will a bit difficult. This is a sequential relative attention. this do some changes on the self-attention with relative embedding. You just add just remember this formula. This is attention, A is attention, and when computing the attention, you just consider the.
No, by the way, Yufan, so in this paper, what tasks are you talking about?
It's talk about 3 tasks I will introduce later. It's
By
just
the way, so it's just for now we're just talking about the input embedding, right?
input embedding. Here is the input embedding. Now we talk about the relative embedding, relative distance.
Or the positional embeddings of the
position embedding. Here is the position embedding because it is a relative position embedding. Could you understand it? It considers the position, so it is a position embedding. It considers the relative position.
Okay, so basically we better to provide their position on the tree, right? Their relative position on the tree, which layer it is, or what, or which symboling, or what kind of symboling node do they have? Maybe you can keep going on. I'm still trying to keep thinking.
Yeah, okay, maybe it's a bit confusing. Now we have a transformer model. Yeah, so now we want to use the transform model in our task. And then the special for the code is that the code is a more like a AST tree. It is a tree, it's not a sequence. So as the transformer is best for the sequence, so we now want to change the tree to a sequence. Okay, so I will introduce 4 works. They all want to change the code to a sequence.
Want to change the code to a sequence. Okay, so basically maybe I still have some ideas thinking about how to embeddings. Maybe you can go through all these 4 solutions and I will have my comments.
Okay, so then we will have a sequential relative attention. Here, this attention just add some weight regarding to the position on the attention here. So remember this. This is
why in this case, why don't we adopt the normal positional embeddings? Since the tree has already been translated into a sequence, right? And so each token can using the original positional embeddings as what the classical traditional transformer does.
Yeah. But he want to do some change to make the performance better.
Okay, so here
this is the query. This is the key, and he want to add a learned embedding for relative position I minus j here to change the attention. Any question here? I think it's just a simple idea. You want to change the attention regarded with related with the relative position. He added some information with.
But there's still some E have here, right?
Yeah. Because this is the value. Okay, this is the value. This is the key. Okay.
But here, sorry. So I have a question here. The EI minus J. So it will be, that means that the embedding of E will be calculated dynamically, right? So that means giving any position I and any position J, we will generate EIJK here.
Yeah. A new key, a new embedding. Yeah, just like we have talked about. He used the WQ, WK, and WV to generate QK.
So it will just abandon. It will actually just abandon the positional embeddings in this solution.
Yeah.
So yeah, because the positional embeddings is actually just play such a role, and now it will actually remove the original positional embeddings and introduce a matrix like EI minus J, so that it just be there. Okay.
Yes. Okay. So here is another way to use relative attention. This is what we have talked about. Here he used just change here, just multiply with a new scalar number.
Just like temperature, right? Just using the temperature.
Yeah. I was thinking.
But yeah, now my question comes to how do they calculate EI minus J and RIJ?
No. They are not here. This is the previous one. This is a new one. Okay.
See, how could it be this previous one? The transformer does not have EIJ, right? The relative transformer does not have EIJ.
Oh, the second formula. This formula is what is the last work. It's not the tree relative attention.
Yeah. So my question is just asking about the last work, EIJ. How do they calculate EIJK? So that means
this work I just talked about. He used a WK, use a WEK, the new weight matrix to get a new,
So maybe I raise an example here. Suppose there have the tree. So 1, 2, 3, 4, 5. Okay. So if we go the depth supposed to be 1, 2, 3, 4, 5, right? Suppose we want to calculate the weights 2 and 3. Now how do we calculate EIJ?
He considered the second and the third node has a edge. So how to compute the edge? He just used this two node embedding to go through a weight matrix and get the final E.
Yeah, it is actually learn, right? It is learn.
Yeah, it is learn.
But in this case, this technique is nothing special to the code. Even for the original NLP or natural language, they still can apply this technique. You can think about it. So there's nothing relevant to the tree structure, right? Once we got the sequence, okay, so you get it. So this is actually a sequence. So basically, it's not it's independent or irrelevant to the tree structure in a way.
Yeah.
Okay.
It's just the upgrade of this work. This work just travels it in some order, and now he changed to the relative order, the relative position.
Okay, they apply the sequential relative attention, and basically I still have a question too about the depth first traversal about the tree, because once we have converted a tree into a sequence, it means we already lost a lot of the node structure, because tree can be transformed into a sequence, but not vice versa, right?
Yeah.
So in this case, if we do not keep the tree structure and just apply some arbitrary relative positional embeddings, actually does not. Why not we just taking the code sequence as a sequence, and why bother we look into the tree?
I also don't know. This is a baseline.
Okay.
Okay. So here we now look at the tree. So how to incorporate the tree information? He used the tree relative attention, but I think it's quite simple. It just use the shortest distance between two nodes. So like U means up, D means down, and here is the distance between like the fourth node and the fourth node and the sixth node, and then use this signal to generate a RIJ number and incorporate in the attention. That you may think it's quite simple. I think maybe you just try many ways.
No, it's not reliable. Frankly speaking, I don't think this is very straightforward, because the tree structure could be very complicated, but from a semantic point of view, it could be very simple, or vice versa. It is just, I think we need to look into something more. But anyway, that is way for, I don't know where it is published, but I don't think just going through the tree here, and suppose I can write a very complicated structure like N1 chord, N2 chord, N3 chord, right? These steps could be very, very long. But this kind of method call may not mean anything there.
Yeah, in experiment, it actually, limits the depth of the tree.
Okay, keep going on.
Okay. And now it's a bit simple one. It's a tree position encoding. It also wants to incorporate the information from the tree. And now he just from the root, from the root to get the information. So he, like, the first node is 0, it is the root because so it's all 0. And the second node here, it is the first is 1. So it's just from the root. So the difference between this work and this, the last work is, this is from the 2 nodes, and this is from the root to the nodes. And you just use some mechanism to get a encoding, and use this encoding to change something. Okay. And this is GGNN. I'm not very familiar with the GGNN because this is used actually the GRU in the graph neural network.
No, GRU is not a graph neural network. GRU is just you apply the GRU in GNN.
Yes.
Okay.
And I think the paper is not quite good. I checked the review, 2 week accept and 1 week reject. And this week I reject actually, he has many works on this field. And this 2 week accept has only 1 paperwork on this field. So this work actually not very good from my side. And for the details, he just used 4 relations. He regards the tree as a graph, and there are 4 types of edge: the parent, left, child, straight, and the self is itself. It is just the self edge. So the GRU means for different type of edge, it has different type of GRU. That means there are 4 GRU. Okay. It's a bit, not very. If you want to look at the details, I refer to the original paper. The first is that if 2 nodes are linking, maybe it's like the child information. So he used a linear layer to aggregate the message, and this aggregate way is a child GRU. I think it's a bit difficult. If you are interested, you can refer to the original paper.
You can keep going on.
Yeah, it's a bit, you must first understand what is GN and what is message passing. And then each message, maybe I can just a short introduction. Like here is the 3 node. Maybe he linked to here and he linked to here. So in the first message passing, maybe like V1, V2, V3. In the first message passing, the V2 have maybe do a linear layer to get a new, unit Z to E1. So after the first chain. After the first thing, the new embedding of the V1 is like this is maybe R1, which is R2. It's like R1 multiply V2 plus R2 multiply V3. So because these 2 edges different, so I is actually different. This is the message passing, the simplest message passing. And for this work, it has 4 edges, and there are R1, R2, R3, R4. and it will in every every batch, the V1 will get the information from different from other words related to it. Okay, so you can just think it is a bit like graph neural network, but he used the GRU to aggregate the information. Okay, so now I will introduce the 3 tasks. The first task is we have talked before. It's variable misuse. Given the code of a function, the task is to identify 2 positions with 2 pointers. One is to show a wrong variable is used, and the one is to show a correct variable can be copied. If it is non-buggy, it's the first pointer should select a special non-bug position. So in this task, it just apply 2 position-wise fully connected layers after the transformers to get the 2 pointers.
Will you please more specific on the position-wise fully connected layer? So maybe we can.
Hello.
Maybe I'll write something simple here. Suppose we have int a equals 1, right? So writing b equals a plus 1 and int c equals b plus 2. Okay. Suppose we change b into a. Now we make the code buggy, right?
Yeah.
And so suppose this is position 1 and this is position 2. Am I right?
Yeah.
Or these 2 positions. Maybe you can be more specific because this is variable definition 1, definition 2, and this variable use, right? So how do we look into the position here? How do we define the position? Pointers, you mean the or to be more specific here, and how these fully connected layers be constructed?
I think it just use the sequence input to the transformer. Okay, then you will get a sequence of that. Okay, then you will use the transformer to generate. Okay, that's the 2 different. So the first feed forward feed fully connected layer to generate the variable 1, and the second is to generate variable 2.
So what I mean is that giving this piece of code, we transform it into a sequence.
Yeah.
T1, T2, and Tn, right?
Yeah.
Suppose this is not too long, and then what's supposed to be, and we feed into the encoder E.
Yeah.
And then we have the
transformer actually feed word to the transformer.
Okay. Anyway, so and here is the decoder, and what decoder is supposed to be output?
No, the decoder will output also a sequence.
Okay.
Is the Z here, a Z sequence, and he will use the fully connected layers to predict which position, which T, if you use the T, not B, which T. Okay.
Sorry. So when we have the encoders, and the decoder will still output a set of the embeddings. Is that what you mean?
Yeah. He used the, maybe we go back to the transformers. He used the, because the final dance is for output the
in this situation, this dance layer will actually derive a vocabulary, one word in the vocabulary, right?
So now we don't need this dance. We actually replace to the fully connected layer and the output.
But dance layer is still a fully connected layer.
Yeah, it's actually the same. So it just outputs the sequence size vector. He just changed the
it will output 0, 1.
Vocabulary size to a sequence size. Okay.
Wait. The sequence size. So here, in the original transformer, for each token, it will represent a vector of vocabulary size, okay? And now each token will be translated into what?
Also the vocabulary.
Also the vocabulary size.
Yeah.
And what is vocabulary size of the code? And the task is that we're going to point out
Vocabulary.
which token or which variable is misused, right?
Yeah.
And how do they represent the problem structure based on the model? And what is output? So still a sequence to sequence model, right?
Yeah.
So maybe I'm going to just simplify the questions. For folks, let me ask question by question. First, whether the decoder will still generate a sequence, yes or no?
Pardon, please. I just
whether the decoder will still generate a sequence.
No.
It will not generate a sequence. So what decoder are you going to generate?
The decoder will generate a sequence of Z, and this Z will input to a fully connect layer to get final one vector. This vector is 1 multiply sequence size. Okay.
Okay, so based on your instructions, so it will have Z1, Z2, and Zn, right?
Yeah.
And given the Zns will be input into a fully connect layers.
Yeah.
And it would output as
sequence size vector.
Sequence size vector. So would it be followed based on my understanding? So this is for fully connected network. But I'm still quite confused about how does the presentation going to show which variable is misused? And can you present what is embedding there and how to model or represent which present information that
because
which variable
now
is
the code is
misused?
the sequence. You just show which position is wrong.
Okay, so what is output? How does the output of the fully connected layer look like? Can you draw something like this?
It is just a sequence vector, a sequence size vector, just like here. You can just think it's 1 multiply sequence size. I don't understand. Actually, I don't quite understand your question here because your output is actually 2 pointer. 1 pointer is a position, you know. A position show where is the wrong variable. And then
so for example, suppose the sequence size is maybe 100, right? So the decoder will generate a sequence size of 100 plus times 1, right?
Yeah.
Or 1 times 100. So suppose the position 0 is 0.9. It means that the first token is misused.
Yeah.
So is that how? So if I understand correctly, that is what I mean.
Yep. Yes.
But what if it were just to point out the int is misused? It makes no sense, right?
Yes.
But it's still possible that I suppose it also point out why is misused, the equals, the simple equals is used.
Yeah, yes. Or maybe I don't know. Maybe I think it is you can, you know, have a upgrade on this if you just filter out the importable tokens.
Okay, let's keep going on. Okay. So, but I think just this modeling or this task is a little bit weird and it's not that accurate. Maybe that model is just for academic use. It can hardly be practical in industry level or for real practical use. Okay, let's keep going on.
Okay, because maybe the model should understand some token is importable. So
I just feel that the model the output presentation does not make sense to me. And maybe we can keep going on anyway. That is formulation there.
Okay, here we talk the second task is function naming. So given the code of a function, the task is to predict the name of the function, and the paper just use the classical sequence-to-sequence transformers architecture, output the function name word by word.
Word by word. And how do they construct the vocabulary?
This for my understanding, this is just a vocabulary size. So he has a vocabulary of word function name.
Okay.
Yeah, just like what we have showed in the before picture. Let me show. Yeah, that's the here. That's the vocabulary size of function name, and he will show which word is for this function. Okay. Okay, so this is the function naming, and the final task is code completion. So the code completion just predicts the next node in the depth first traverse of AS tree, and there are two types. The first is the type, and the second is the value. He just used two fully connected layers, so to predict the the tokens.
Wait, so in this case, it's still output. How does it decode output?
There's the vocabulary of code. He just output one possible, the most possible token in the vocabulary.
And how does the import is going? Because since it's a code completion, they need to remove some tokens, right?
Yeah, I think it's used maybe mask.
But anyway, so suppose that I'm going to write a code like int a equals a square and int b equals maybe floor a, right? And it's going to fill things, and this log could be anything there. But it could be a very long expressions, could be a constant, or could be a method call.
Only AST node, AST tree node.
Yes, I mean that only one node. So it means it has to be the leaf node.
Leaf.
If it is a parent node, all this leaf node will be deleted, right? So it means that it can only delete this one, not this one.
I don't know actually, because I'm not very familiar with the AST tree.
Okay, maybe we can keep going on. So let's look at how they conduct the transformer imperial study, and that'll be some useful information for us.
Yeah, here is the data set, and the data can be downloaded in the GitHub. And he used a Python and the JavaScript two program language. And here is the experiment result. Yeah, here is a question: why GGN is not applicable for the code completion? You know here. I think you can. This is answer the question. The Dr. Lin just ask. Anyone have any? Maybe Dr. Xiao Yan. Anyone have some?
Yeah, sorry, I don't know.
Okay. From my side is that because the GGN has message passing, it's used the total ST tree. So the message passing involves all the nodes, and so it prohibits using masking in the decoder. So you can't mask the one node. Then if you mask one node, there's no message passing. There will be, so it will have no experiments on the code completion. Maybe I go back to. Anyone have some question? If you if you just mask one, the message passing will stop. Maybe I draw a graph. Maybe I use this graph. Like here, here is a tree. If you you think if you just mask this one, so this node will be not exist. And so the magic passing, like this is a family, this is a parent, this are children, this are children, this are children, this are children. So the information will not passage to this node because this node didn't exist because you mask it.
Okay, let's keep going on to see more of the results. And what does this empirical study tell us?
Okay, so in this experiment result, you can see that if you're using the tree information, you mean the AST tree information in the variable misuse task, the performance is not quite effective. But if you use the sequence relation attention, that means you do something on attention, it will be much good. So the paper thinks that utilize the structure information in the input embedding is not effective. And but if you utilize the structure in the self-attention mechanism, it will be much more effective.
Does it mean that in the self-attention layers, if we put the tree embeddings or tree position embeddings on the self-attention, that becomes a little bit more effective?
Yes. But if you just do some embedding.
Have they applied some statistics analysis?
No, it's just
calculate an average, right? Or the average the average accuracy.
Yeah.
Then the result does not seem convincing.
I also think it's not quite convincing.
It's not convincing. So we need a way, but just from the methodological point of view, I don't think one approach seems to be have an obvious advantage of the others, especially for variable misuse and function naming. And also, I don't think they model the problem in a very precise way. Right, think about it. So anyway, you can input some variable, you can input some assignment operations or some keyword operation, keyword tokens as they misuse, right? And also when they are extracting the sequence, they do not consider some date flow, control flow, etc.
Yeah, they think the data flows, these things may be the future direction.
Maybe we can talk with you later about how to model the program or model the code. I think it is not realistic. Maybe we can discuss this later. Let's keep going.
Okay.
But anyway, I think in this case, I think think if their information is not that intriguing, maybe their writing must be very useful for us to refer, because we're supposed to have empirical study as well in the future. So in this case, I suggested we look into how they design, how they choose the task, and what insights they provided based on those experiments and study.
Yeah, I think the most analysis is just a subjective analysis. So I don't think it's quite convincing. For example,
and so what is the takeaway? What is the takeaway? So they have the tasks, they evaluating different embeddings, and what is the takeaway?
Yeah, the takeaway, I have just shown that the first is that the existing approach focuses on capturing tree structure and do not investigate the influence of other components of S tree, like the types and values. The second is that emphasis the sequential relative attention because the experiment should compare with the 4 methods. This is the most effective one. So he thinks that sequential relative attention is the most effective and the most important thing to capture AST structure. And he also do an experiment on the compare with the syntax and the text. If you add both, syntax and the text, the result is much good.
So how do they add the syntax?
Oh, the syntax just the syntax of AST tree. The text is actually the tokens.
So how do they how do they present the embeddings? So my straightforward thought is that suppose that suppose the token that int a equals 1, right?
Yeah.
So int will be an embedding like e1.
Yeah.
And another concatenation e2 means that it is actually a keyword or type, whatever it is. And a, suppose this may be the keyword, and a means a variable.
Yeah.
And but how about? But anyways, for this node a, it can be considered as a variable name, and also considered inside a variable declaration, and also to be considered the expression of the variable assignment. And how many syntax will be used in this variable?
Just the AST tree node you can see here.
So you can see, so suppose we write something, it's something like int a equals, sorry, it's not here. And then suppose variable, this is int, and this a equals 1, right? Yeah. So this a have many parent, but suppose we're looking a, the first parent is, for itself, it is a variable name. And for its parent, it's a variable declaration, and for its grandparent, it is a variable assignment, right? And what did it choose?
Yes. They first traverse this syntax tree. Okay, since traverse this syntax tree, and if there's no text, it is just empty here. You can see it is have some element. You input, you change the text field to an element. Okay. So he consider one node as one, one part, one neuron to input, one node. And this node, maybe it has some syntax, and maybe have some text. It will concatenate. Okay.
But in the AST, there's some virtual node. It is not some text, and it will also for some virtual node or some placeholder node. Will this kind of node or is this kind of dummy node be an input of the input sequence of the model? For example, just what I mean that. So this node is actually a virtual node, right?
Yeah.
And will this virtual node be one of the input of the
yes. Yes. Because the text is just empty.
Okay, let me think about it. I think this is not the best way for encoding the AST. I think and I think when you had here, he mentioned something called the tree capture, the model tree capture to model the tree structure. But I still think about it, what is the best way to encode it? And also, I think for AST may not be, it depends on what task. For example, if we want to have the variable misuse, I don't know whether the task of variable misuse makes sense. It is because since there's no specification for the code, and for example, if I write a code like int a equals 1, and int b equals a, and int c equals a, right? Suppose we change a into b, and why? And in what sense that it means that this piece of code is incorrect or buggy?
It is a training, so it has golden labels.
I know that it always have a golden labels, but whether this golden label actually makes sense. If I change A into B, it is bug. You think it's misuse, right? It is misuse. And why do you think code is misuse? In one project it's a bug, and in another project it's a feature. Right. So in this case, I don't think the task of variable misuse actually makes sense. Right. So under different scenarios, it can be buggy, it can be not buggy.
Yeah, maybe.
Yeah, I think we need to think very, very carefully about the pre-training tasks. Maybe the code completion is important, and then also if we want to work more on the code generation, I think since you have finished the presentation, I think we have finished this. I just have a few comments here. The first is that the code representation is always a problem. I think transformer is a very powerful model for us to work on very different kind of software engineering tasks, code completion, debugging, or code summarizations, etc. But how to effectively represent tree or represent code is still a very open questions. And here in this paper, they look into AST. And the idea of AST still exists in natural language, right? Or natural languages, we saying that good morning, and morning is supposed to be a noun, and good is supposed to be an adjective. And it can be also considered as a tree, right? So the information of AST has been widely, or the concept of syntax have already widely been applied in the natural language processing. There's nothing special. As long as, so I don't think traverse the tree and use it in a reorganized structure would be a good idea. We may just make the code sequence as the original sequence. At most, we attach the syntax information for each token, and that will be fine. I think another perspective is about the data flow control flow, because in the code, basically we want to know more information there. So maybe the data flow, control flow, and the relative semantic information there, or the code duplication information, maybe that will be also helpful. So for now, or at least to me, there is still lack of good technique for us to modeling the code, right? So whether the code can be well modeled, maybe tree is a good idea, maybe the graph is a good idea, maybe the sequence per se is already good enough to do a lot of tasks. So maybe we still need to dive into more details. What kind of the permutation can we do? Maybe positional embeddings, maybe graph embeddings.
It shows that the sequence is just enough, because the sequence relation attention is the most powerful one.
Yeah, I agree that. And also whether, so my follow-up question is that whether AST, I mean the sequence here is the sequence information plus AST information, right? So it is still provides some AST informations, provide AST information to the sequence information, right?
Yeah, I just show here. You can say that the syntax information is the AST tree information. The text is just the original. And
yeah, my point is that there's also no need for us to input this such a virtual node. You can see that this virtual node have two children, int and a. What I mean is that there's no need to input this virtual node into the model, and all we need to do is just to attach more syntax on int and a. So that is my point.
Oh, okay.
And also, suppose we have borrowed the idea of int a equals 1, and suppose we have semicolons, and then we input b equals a plus 1, whatever it is, we can further build a relation between this a and this a, and maybe a semantic information, or maybe we can even borrow the meaning of this a and this b and a. We can provide such more strong relations to tell the model how relevant, or so usually we hope the model can learn the relevance between B and A. But in this case, there's no need for it to learn it. We can just pre-train it. We can predefine the relationship. In this case, we can avoid a lot of computing power. So that is another way to encoding or providing more information from the code, right?
Yeah, yes.
Just think about it. So just you write a sentence like the animal does not cross the street because it's too tired, and the it will be referred to the animal. And in the natural language, we need a human to infer this information, but in the code, there's no need for us to infer it. because the date dependency of the compiler already tell us this information. So maybe we can just encode it and encode such relations into the model, and that will be more helpful.
Yeah, I think so.
Okay, maybe let's talk about this later in our individual meetings. And for Yufan, the most important task is that we finish the code summarization work and have a submission, and that will be very helpful. And also, we're really looking forward to the differential analysis for analyzing an arbitrary transformer or model. Since this talk is actually a little bit long, should we wait for 5 minutes and I will be back in 5 minutes? And Siang Hwee, would you please share your slides first? Okay. Let's have a rest, and we're gonna start at 5 or 4:15. Okay. Siang Hwee, would you please start?
Yeah, okay, can. Okay, good afternoon all. So today I'll be presenting on this paper, Synthesize, Execute, and Debug, Learning to Repair for Neural Program Synthesis. So these are the authors for the paper. So they all have a focus area in like machine learning and machine learning and some form of programming languages. Yeah, so you might notice that they are all from different schools, but this paper was actually written when all of them were still at UCB. So that was how they came together to collaborate on this paper. Yeah.
Okay, at that time, the first author is undergrad student in UC Berkeley.
Sorry?
So you can see the first author is a PhD in MIT, right?
Yeah, yeah.
And
He was,
mean that so
he was
that he conducted.
I think he was an undergrad student at UCB at that point in time.
Okay.
Then
so his work is conducted. This work is finished when he was undergrad student in UC Berkeley.
Yes.
Okay.
Yes. Yeah, and over here Peter Ebert is he was there on, I believe, on exchange or something like that. Yeah.
I see. You can see, so now in the top universities in United States, usually the undergrad students begin to publish top tier papers, and then they come to the become a PhD and at the top university. Oh, by the way, which venue this paper is published?
Which venue? Like
which conference? Which conference?
Hold on. I think it was the NeurIPS.
The NeurIPS, right?
Yeah, NeurIPS.
Okay, let's keep going on.
Okay, yeah, sure. Okay. So the background for this project is actually heavily focused on program synthesis. So program synthesis is actually a very up and coming problem that people are trying to solve with machine learning or AI. So the idea is that given certain specifications, we want the algorithm to actually generate the program for us. So in most cases, it can be something like we will give the algorithm the input and the desired output, and then the algorithm will output the program itself. So this program synthesis has been very useful for things like string manipulation and graphics application, etc. Yep. So so prior to this paper itself, there has actually been quite a lot of work on program synthesis. So some of the more recent findings were that if we use the execution results, the intermediate execution results to guide the program synthesis, it actually performs a lot better. So the idea is that, let's say we have a very the initial program that is generated, and we run it, and then we use whatever results from there and try to predict the rest of the program, and that actually improves the accuracy of the program synthesis itself. But this method is actually very suitable for sequential programming, but it's not very suitable for programs that actually contain loops. Because if there are loops in it, the execution results of a partial program of a program that contains loop might not be informative. So what I mean by that is that, let's say that I have a line over here. So it's a very simple while function. So while there's a condition, we do a certain action B. So actually this while function would be converted into something like this. If it's C, then you do B. then the next part of it, this part here is actually like a recursive call. Else we just do not run anything. So this is how this while function would actually be translated into if we are looking at it from a partial programming perspective. So notice that if we are to do like a partial programming, this while function might only be executed once, and then we cannot actually gather the right information from it. So for example, maybe this while loop is supposed to run 5 or 6 times, but because we are only running it once, the output might not be accurate. Yes. Okay,
the partial execution. So so let me rephrase here. In the priori work, and it's still given a set of input and observe their output, right?
Yes.
And assuming that we want to generate programs with loop information or with loop structure, and the problem lies in that suppose the loop supposed to be run 5 iterations.
Yes.
But if we synthesize a program like if C's and whatever it is, the result will not match.
Yes, correct.
So here maybe you can mention a little bit about the priori work, how and how this can work for the sequential programs if there's no loop, and why the program execution will be informative. Would it be clarified for this part?
Why if it's a sequential programming, this would work better, is it?
Yeah.
Is okay. The idea is because okay, I never dive into the prior works in very great detail, but I believe that because we are doing sequential programming, actually it's a line by line thing. So based on the results that we get for that block. So for example, let's say I'm doing a simple program that does like some form of addition, or maybe a few lines of addition. If I do it because it's sequentially, I can actually get the results for each of the intermediate lines, and based on that, I can predict the next.
How can I get it? So maybe I can be more specific. Since you do not dive in it, maybe you can have a brief discussion on this part. So assuming that we have a test case, suppose we have an input like the input, and suppose when it have 1 and a 1, and output 2. Suppose it has 1 and a 2, and output 4, and suppose it has 1 and a 4, and output 8. Whatever it is, so I just make up this number because there have a number of the programs which can allow us to have this input and output. And assuming that we're not synthesizing any program with loop structure, so whatever it is, I try to write something like suppose input and x1 and x2, and I try to whatever it is I'm return x1, right? Suppose in the very beginning I can return arbitrary program like this.
X1
right? Correct. So in this case, we know that the first is passed, right? And the second and the third will fail. And then anyway, so this kind of feedback, right? And it can provide some information for us to keep improve or right. So in this case, I will try to evolve the original program, like if maybe x2 equals 4, we'll try to return 4, right? And anyway, any other case we return x1 plus x2. So this is another program that try to evolve. So that we can be, this will be passed and this will be fail again, right? So whatever it is, so giving the pass and fail, we'll keep synthesize the program and evolve the program until all the test cases will be passed, right? So that's basically the program synthesis we want to do. So I'm not sure whether I'm saying the correct way and why this idea cannot be. And then I'm a question that anyway. So this is my makeup procedures.
Correct.
So my question is comes to how does this intermediate results will be used for analyzing to improve the program synthesis.
Okay. The thing is it doesn't do it like that. So how should I put it? So another problem with the current works is that the moment that the program is inconsistent, it actually just stops. So when after they generate the program, they actually don't do like a test, and then after that they do a debugging and stuff like that. So I believe that this intermediate result is, let's say I have a very long program. So for example, like maybe my input using your example is like 1 1, and maybe it comes out with 2. So let's say it's a very long addition algorithm, okay, like a very long addition algorithm. So there are multiple lines, multiple steps. So each of the steps has intermediate results to it. Each of the program line inside has intermediate results to it. So because of that, based on whatever results that I get back from my current line, so maybe I have line 1, line 2, line 3, and on, right? So based on what results I get back from 1, I can do some form of prediction for line 2, what needs to be done for line 2. So for example, let's say, okay, let's use this example of 1 and 3. So if my first line is like a addition, then based on that, I get 4. Then maybe I need to, my second line, because 4 and 8, there's quite a difference. So maybe my second line is, so maybe the first line, the program synthesis is that it use x1 plus x2, correct? And then after that, it chooses, because here I get the result of 4, my output is 8. My intended output is 8. So maybe on the second line, I will do this, the value from line 1 multiplied by 2. And then in that way, I sort of get the desired output. So that's how it makes use of the intermediate results to predict future lines. Yes. So because it's sequential, it's actually very clear cut. But if let's say I have like a while loop, like how many times I loop in the body of the while loop is not very clear cut. So they actually, it's not very suitable in this manner. Yes. Yeah, so I believe this is more of what they were referring to, the intermediate results.
Well, the point is that this is for one test case, right?
Correct.
The test case is given input, and we have the supposed or expected output. And then suppose we have suppose the final output is 8, of course, we can multiply it by 2 and we get 8. Correct. But in this case, suppose the another output is actually 2.
But I got 6.
No, what I mean is that suppose the output is that given it 1 and 1. We got 2 here. Suppose we got a 1 and 1. Correct. We will have 2. And we got a 1 and 2, and we got maybe 3, and whatever it is, 5. And then the final output is supposed to be 2. And when we have the intermediate result 3, we're supposed to get a 4. When we had the intermediate result of 5, we're supposed to get an 8, right? Correct. So how do we keep synthesizing? Because we not modify or synthesize a program based on a single sample. We need to optimize the program or evolve the program for multiple. For all the data set. The data set means that all the inputs. And how do they do this?
Okay. So yeah. Like I mentioned. Okay. I guess how they can optimize this is, let's say I'm doing line 1, right? So I'm doing line 1 over here. Line 1 would take in all the inputs, and then based on these intermediate results, the second line would try to match as closely as possible the intermediate result to the desired output. So so let's say here I have 3 examples. So I have 3 examples over here. So maybe 1 1 gives me 1 1 gives me 2, 1 2 gives me 4, and 1 3 gives me 8. So based on all these 3 results, I will pass it into the first line of the code itself first. So maybe the first line is an addition. And then based on this addition, maybe then it can try to generate out the second and third line. Yeah. So maybe based on, let's say, line 1, right? Based on line 1, if I pass in all my input values, so I'll get 2, 3, and 4.
2, 3, and 5, right?
This is 1 3, right? Or 1 4. Okay, and then 2 3 and 5 is assigned to. Yeah, then maybe in the second line onwards, because they want to try to make as many of their test case as possible to hit the desired output. So they can maybe take a look and see what line would bring it as close as possible to the desired output.
And how about synthesize the if condition? Whether they can synthesize the if condition, like if then statement.
This if condition, but okay, so this was mentioned in the prior works. I'm not too sure how they handle the if condition, but I believe like in our case, we can do something like if the value is equal to 2 and then we return, we can already return it or something like that. Yeah. So the idea is that based on the results I get from my previous line, then I will try to bring as many of them as possible to my desired output. So I guess that's why it's suitable for sequential but not for loop.
But the point is that I think the same ideas can be there, right? Suppose we write a loop. So I tried to clear all the cases. So assuming that I still write again 1 1, where I have 2, and 1 2 have 4, and a 1 4 where I have 8, right? Suppose this is the input, and suppose we synthesize the loop here. So assume that the loop is synthesizable, right? Loop x is smaller than 5, and x terminated, right? So then, as long as we finish the execution, and the intermediate result will be none, right? Then we just, for example, suppose x start with maybe this x1, x2, x1 plus x2, maybe equals plus 2, right? So x each time of iteration, x will incremented by 1, and x2 will incremented by 2, right? So getting 1 1, and again 5, x1 was supposed to be 6, and the x2 was supposed to be 11. Right? Right. In this case, we can keep going on, right? If it is 2, we can synthesize another because it's final output 2. So the intermediate result will still be helpful in this case as long as we finish the execution of the loop. And why these things that are not suitable for the loop?
As in, so your what you're trying to say is that so long as I finish the while loop or whatever loop that I have, based on the output itself, that information is still informative.
Yeah.
Right. Okay. Yeah. I think I agree with you on that this information will still be informative. And to be very frank, is that this paper seems to be tackling this issue more. The idea of debugging instead of handling stuff like this. Because I feel that the while loop, they didn't really explain how they handle it or how they choose to solve this problem. Yeah, they only mentioned that it's a problem right now, and maybe their debugging aspect is able to handle this.
Okay, so maybe I can rephrase it here. We do not, because we have limited time here, and maybe I can just hear. For here, training synthesizer program is very much like training a deep learning model. But the deep learning model is trying to adjust the weight, or the structure has been fixed, and we're going to keep evolving or updating the weight, so that we can make the input and output will be match, right? And here it's very similar. We have input like x1 and x1 equals to 1, x2 equals 2, and we have a final output 2, 4, 8. But we are not training a neural network model. We're trying to synthesize a logical program. So we hope that the structure include loop, including maybe method call or maybe something else. So we will have check whether we can do something like this. But of course, some more complicated cases, maybe some more complicated specification like sorting the array or generating a graph, so that will be more complicated. So this may not be described by a neural network model, but it might be helpful by the program synthesis. But anyway, the program synthesis is still in a very initial stage.
Yes.
Okay, keep going on.
Okay. Yeah. So yeah, roughly I think because the loops makes the whole program very complicated. So it's not very informative. It might not be informative. It can still be informative, but it might not be informative. Yeah. Okay, and the second problem is that currently the current method is that it generates the entire program from scratch. So it just does a synthesis to execution. It doesn't actually do any form of debugging. So even when the program is inconsistent, the algorithm just output that program. So even if it's inconsistent with like maybe 20% of the test case, it will still output that program. And that's where the man in the loop will come in to go through the code itself to fix it. So yeah, that is actually the main focus of this paper, is that they want to try to remove the man in the loop problem by including a debugging phase into this synthesis itself. So the idea is actually to synthesize the program. After they synthesize the program, they will execute the program, and then based on the execution, they will try to debug the program. Yeah, the main focus of this paper is actually on the debug portion. So it's actually inspired by trial and error human coding procedure. So they were, okay, from a synthesizing perspective, it will actually synthesize a few programs. So that's what we call like the candidate programs. And then after that, we will execute the different programs, and we will select the most promising candidate program to go for debugging. Yeah, then it's like a recursive process that they will keep generating the most promising program to go for debugging. Yeah. So it's actually made up of two different components. One is the synthesizer itself, and one is the debugger. Yeah, so the rough execution flow, which I explained, is that first we will synthesize the candidate programs. So there are multiple of them. And then after that, we would execute them to see if any of them satisfy all the constraints. So if there is one that managed to satisfy all the constraints, then there is already a valid program. So we can stop over here. If not, we will debug the most promising program, either modify it until it satisfies or it hits the maximum number of iterations. Then
this SCD involve human effort.
No, it's trying to remove human effort. So the idea is that the debugging itself is done by an algorithm also. So actually the main add-on that they have to this whole program synthesis is their debugger. So that is something that they are trying to implement over here. Yeah. Okay. So yeah, and I think that is what is also valid for our use case. Okay, so the idea, so there are actually two problems that they are trying to solve over here. So one is that given some input and some output examples, I want to synthesize a problem. So the synthesizer model is provided with a set of input-output pairs, which can be referred to in this manner. So it's just k examples of input and output pairs. Yeah, so the synthesizer model will try to generate a program such that for all the input here, for all the input that is given, it will try to give the valid output. Yeah. Then
what is P and a ground truth?
So P star is just a ground truth program. So let's say because this is like a machine learning training, so there is a ground truth program which is able to handle all the test cases. So the algorithm doesn't have the ground truth program P star, but it would want to generate a program that is that produces the same output as
here's a okay, so
so the idea is that the ground truth program itself must be able to produce all the output to be correct. So I mean, if there's no ground truth, then maybe the input output pairs are not valid.
Darren have a question here. Since so doesn't the programmer have to write a ground truth program anyway?
Okay, so
so maybe I'm going to answer, I can help answer this question. So this is for experiment. So anyway, we need to know a ground truth program. Of course, in actual case, there's no ground truth, but in the experiment or in the methodology design, we need such a ground truth to see, assuming that we know such a program, but at least we know such a ground truth program exists. And when we're using this program to generate a set of the, or a large set of the input and output, whether we can synthesize another program, have exactly the same behavior. And of course, so given a set of the input and output, there have multiple versions of implementation or algorithms. So that is why the third bullet Siang Hwee mentioned here is that suppose we have generate 100 input and output, 100 pair of input and output, and we synthesize the programs which can perfectly match the input and output, and then we can using the ground truth to generate another 100 pair of input output to see how general or whether the synthesizer program can be generalized on the additional pair of input and output. Have I explained it?
Yes, correct.
Okay.
Okay, yeah. I think just to add on, so actually there are two ways of interpreting this goal itself, which I will touch on later, but since it's brought up at the moment. So actually for this P that we are trying to generate over here, this program P, we are actually, it can be a generalization metric or an exact match. So generalization means that for all the input and output, I actually get everything correct. So that is, it can generalize well. But an exact match means that this program P that I generate is the exact same.
It is more like it's more like the overfitting problem in machine learning. So giving the input 1 and 1, so and getting 1 and 1 it output 2, and giving 1 and 2 it will output 4, right? In this case, we can write the most trivial way to synthesize the program is like if x1 equals 1 and x2 equals 2, then we return 2, right? And then similarly, if it's 1 and 2, and we return 4, right? So this program can perfectly meet the expectation of this input and output, but definitely this is a very trivial implementation or very trivial result of the synthesize. And we hope there's supposed to be a general function like maybe return whatever it is, an x1 to the power of x2, maybe 2, maybe 2 to the power to x2. Maybe this is 1. This might be one way of generalization that may not be correct. So anyway, we still need a ground truth P stop to derive a set of the input and output and to see whether the new generated P, this case is called P, can always, and the input and output generated by P star can always be satisfied by the P here. So this is a general idea, and this is a problem definition.
Yeah, correct. So the second, so just to prevent the cases like we mentioned just now from happening, there is normally a test set that we will further verify. So it's like a normal machine learning kind of thing. So we will have the so-called training set, and then we will have test set to verify that the program P gets the intended output.
Okay,
then the second problem, the second problem that we are trying to solve, because this paper is also emphasis on the debugging side of things. So it's whether we can repair the problem given the IO specification. So the IO specification is the same as before, which is that we have a pair of input and output. But for this case itself, we actually have one additional input, which is the buggy problem P prime. So the idea is that we want to perform some form of editing so that P prime, the buggy problem, can become correct. So this is actually no more difficult than the synthesizing problem, because if I edit P prime sufficiently, I can actually totally erase the entire P prime and write in my own P. Do you all get this part here?
Sorry, so will you please mention again?
Yeah, so because here I'm trying to edit P prime such that it's as close as possible to a valid output P. So it's possible that during this editing itself, I might remove all the lines of code in P prime and just rewrite a whole P. So it's possible that I go back to the program synthesis problem. Because of how editing is done, I can actually delete line by line and insert line by line. So I can actually, it's no more difficult than the synthesizing problem. It's equivalent to like the synthesizing problem.
But in this case, at least we know the buggy program can satisfy at least a partial set of
Correct.
input output, right?
Correct. Yeah. So that's why this program repair is only beneficial when our P prime, that means the buggy problem is already very close to being correct. So if it's very close to being correct, then maybe with a few edits, it's able to generate a valid program. Yeah.
Okay.
So these are actually the two problems that they are trying to solve. Okay, so okay, so before I dive further into it, actually I would like to introduce you all to a game. It's sort of like a game. It's called a Carrel domain. It's actually very often used in this kind of program synthesis problems because it's very clear cut. So it's based on a programming language that is very similar. It talks about a robot within this 2D grid. So there are certain obstacles in this grid that the robot can't go through. And then I have a robot that his starting state is like this input 1. And I just want him to be in output 1. That's his end state. Yeah. So this over here.
And what is the difference?
Yeah. Over here, this is the start state. And over here, this is the end state. Yeah.
End state, why this is the end state?
Sorry?
Why this is an end state? And what this dot means? The black
okay,
dot.
yeah. So the black dot is what we call a marker. A marker is like it's so this robot, right? This robot actually can do 4 different instructions. So it can move. So when it moves in a forward direction. It can turn left. So after it turn left, it can move again. So for example, right now my robot is here. If I move, it will go straight like that. Then if I turn left, my robot will now be facing upwards. Something like that. So if I turn left multiple times, then I can move downwards. Something like that. So this is it. The reason why a lot of people use this is because it's very simple. So actually you can see that with just 4 instructions, I'm actually trying to describe this describe this problem lah. So essentially from given this input, I want to achieve this output. Yeah.
And this output including the positions of every mark and the position of the robot.
Yes, correct. So the input, I don't know about the input representation, but we can just think of the input as the grid itself, maybe with the markers, how many markers there are. So the idea is that this robot, he can move and then he can place markers along the way and he can pick up markers along the way. It can be a bit more complicated. So in the actual domain itself, the robot has a bag, and whether the bag has enough markers for you to put down or pick up, that kind of thing. But just for the sake of this presentation, actually these 4 instructions that we have here, the move, turn left, pick marker, and put marker is sufficient for our use case. Yeah. So it's definitely a bit more complicated than that. But just for the sake of this presentation, I have just selected these 4 instructions. Yeah. So this language itself is written by a Stanford professor, I think in the 1980s or 90s. And recently, I think previously it was a bit more like Python. A bit more, the syntax is a bit more like Python, but based on what I checked this week when I went to look at their website, it has been revamped to be a bit more JavaScript-like. So I will be using this JavaScript variant, even though the paper itself actually used the more Python variant. Yeah. So I'll be using the JavaScript variant. Yeah. So my first question is how will you move from input 1 to output 1 using this built-in instruction? So think that let's say now you are the algorithm and I give you this input and this output. So how would you move? Yeah.
Okay, so we can pick
anyone,
up
yeah,
and volunteer.
yeah, this is a very simple thing, yeah. Maybe Darren.
My guess would be we just move forward until we hit like this one.
Yeah.
Turn left and go up here, drop the marker, turn left until you point back here and go down again. Turn
Yeah.
left and go.
Okay, yeah. So roughly that's it lah. That's a valid move. Yeah. So okay. So my I have a function here. It's not perfect. It actually, I realized that it actually miss out this dot over here. Okay, it miss out this dot over here. If you look at this function, so this function actually just sends the robot in this direction. Okay, so but I mean this is more like a
buggy.
Yeah, more like a buggy. Okay, so this is a ground truth program that they came up with.
This is ground truth.
Yes, this is the ground truth program because okay, yeah, I'm just bringing this up first because actually there are multiple inputs. So if we recall just now, it's made up of pairs of inputs. So if we look over here, I have input 1, output 1, and input 2, output 2. So you'll notice that this so-called ground truth program is able to handle both inputs and output. Maybe output 1 is not exactly correct. Yeah, but it's able to handle both to a reasonable amount. Yeah. So this is the so-called ground truth variant that we have over here. Is based on the paper itself, this is also the Go program that they are using. So to run through this SED just to make it a bit clearer to people. So how it works is that, let's say now I have a synthesizer. So my synthesizer might be very basic. So it can come out with something like this. It just move forward by one step and it puts down a marker. So this is definitely a wrong output. Yeah, over here, this is definitely a wrong output. So the idea is that they want to try to use some form of debugging where it actually looks through the program itself and determine what lines to keep and what to maybe insert or to delete or to remove. Yes, what lines to remove, replace, or insert, or to keep. So in this case here, we can see that from this synthesizer output to achieve something like this Go program, actually the difference between this synthesizer output and this Go program is that I'm actually moving 2 times more. So that's why over here we can see that they insert the move line 2 more times. And then this program will actually look something like this program. These 2 programs will be equivalent. Can you all see that? Yeah. So
how do you know that we need to insert to move here?
Correct. So that will go down to the debugger itself. So this is just roughly the flow and example how they. So the idea is that based on some buggy synthesize program, they want to do certain edit operations so that I can create a somewhat valid program that is equivalent to my golden program. Yeah. So that's the how SED is meant to work. Okay, yeah, so with regards to like whether to keep or insert, this will be touched on later during the debugger itself. Yeah.
But
so
how this is relevant to loop?
Yeah, so that's the thing I want to say. That's why I feel that this paper didn't really answer the issue of the loops.
Okay,
They answer the
good
issue.
Story there.
Yeah, they were bringing up the many problems, or okay, the 2 problems that is currently facing, and they never really bring up this part. But I guess in this example, we can see that in terms of loop, they are just adding in more commands. So this part here is just a loop, and then they are just adding more commands because the current works itself, they don't do any form of debugging. So the human needs to come in to do a debugging. So I believe that this one, because they are doing some form of debugging, so we can.
So the supposed debugging is more like kind of defining a loss function, right? So
Yes.
we're just evaluating the difference between the expected output and the current output. and then we just try to randomly insert some behavior.
Correct.
Of course, in this carrier programming language, the number of instructions is quite limited, so the combination is still limited.
Actually,
but if we go to some more complicated language like Python and Java, and there's almost like infinite number of library code, and the search space will be really, really huge. And I don't know how to solve this kind of problem.
Okay, yeah. So actually, I agree with you, and that's why I feel that overall, my takeaway of this paper is that it's very theory based. Like in the real world perspective, we have unlimited lines of instruction. So in our case here, because we only have 4 instructions that the robot can do, so it actually becomes very easy to debug. But in a real world case, like what you mentioned, if we use Python or anything like that, there are unlimited numbers. So the actual in practice use of this, I'm not too sure how useful it is. And actually that is one of my takeaways with this paper.
Yeah, so because it's an interesting research paper, but I mean practical in
correct,
the real world.
It's interesting, but I don't think it's very practical, because the whole experiment, like even the experiment that they do, is all based around this idea of
I remember that
this
work is actually published in last year, right?
2020.
In last year, 2020. Correct. So anyway, so this you can consider as a manual or a special way of the optimization based on the program execution. Maybe let's go through these details. Maybe we can have some additional takeaway other than it's in practice.
Sure. Okay. So essentially that's the idea here. Okay. Moving on. So as I mentioned just now, there is 2 portions to this whole architecture itself: the synthesizer itself, which generates the candidates, and the debugger itself. So this paper is actually largely focused on the debugger. In fact, the synthesizer is maybe when they were discussing the synthesizer, is only about 6 lines or so. They were just saying that we can use any of the current synthesizer that employs encoder and decoder architecture. So
the Synthesize is based on neural network model. They use LSTM to generate code.
Yes.
Basically, so you can consider just like Yufan mentioned, given a transformer or given a sequence-to-sequence model, it is just going to iteratively generate some vocabulary, right? And here, there's only 4 vocabulary in this scenario, right? Pick up the mark and put on mark, move, and
turn left.
And turn left, right? So in this case, LSTM definitely can work, but in real case, it becomes far more complicated.
Yeah, I believe that a lot of the synthesizers, they also work based on this model itself, this domain. So that's why I say this domain is actually used very often in this kind of program synthesizer. But I think there is a lot of I don't know how relevant it is to some more complicated programming languages.
But here, one of my comments is that however complicated Python or Java is, it's just basically a Turing machine. It's basically do you know about Turing machine? So it's called the Turing machine. And the Turing machine basically means a state machine, indicating what is the state, what is the initial state, and what is the transition, and what is the vocabulary of the state, etc. So we have a set of the tuples including there. So what Java and Python or carry out, so they are all Turing machines. But the difference is that in this Turing machine, the state space is very limited.
Correct.
But in Java and Python, there's almost infinite number of states. In this case, it becomes more complicated. So in this way, maybe what we focus is not to synthesize a specific programs. What we're looking into is that how to synthesize a state machine to do this. Turing and Alan Turing is a very famous computer scientist. And now there's we have now that there's Nobel economic award, right? But there's no computer science award in Nobel Prize. But the best or the highest award is actually Turing Award. It's going to memorize and to memorize the Alan Turing. So there's Turing Award there. So all these computer getting the unless the quantum machine or quantum program languages, basically it is not Turing machine. But already existing languages, the long as it's using some the von Neumann architecture. Basically, von Neumann architecture is just based on a Turing machine. For now, any program language, any system like Android, IoT devices, desktop, laptop, all the calculations are just based on Turing machine. Just one instance of Turing machine. So that is how greatness about this idea is. So if we talk about a synthesize, maybe we can start with this idea. But here, we may talk about the state change. But anyway, if we just turn into a Turing machine, and everything becomes more formal, and we need some proof there. Okay, so maybe we go a little bit far.
Yeah.
We're going a little bit far away, but I think it's kind of relevant. So as long as we can have a state machine to describe it, and it seems to be a reasonable plan, at least despite it's kind of tall plan, but it might be have some enlightening there.
Yeah, I think but I think another, if the synthesizing part might be hard, maybe the debugging part might be useful for us, because like let's say I have a so-called a buggy program and I want to try to program repair it. Yeah, so maybe that. Yeah, so actually that's why this paper might still be relevant to us. Yeah, but because okay, now I'll move on first, and there are still certain flaws to the debuggers itself. Yeah. So okay, so down to the debugger architecture itself. So it might look very complicated over here, but actually the whole paper is just focused on this red dotted line, this red dotted box. So this trace embed part is the part that they actually came up with that's a bit different from other papers. So other than that, the rest of it, this IO embedding, what it does is just that it embeds the input and output. So after it embeds the input and output, it passes to the edit decoder. So notice that the colors are the same, which means that this is passed directly to this. Yeah. And over here, the program encoder, what it does is that it takes in the candidate program and it encodes token. It encodes the token. So I guess we can think of it as it encodes the instructions so that later we can do a mapping of the instructions to the traces itself. So what instruction will result in what action being taken. Yeah. And then the edit decoder just tells the program like whether to insert a new line or to delete a line or stuff like that. Yeah. Then the key part is the trace embed part, which it actually combines the execution trace of the program along with the input and output. And that will be passed into the edit decoder as well. Yeah. Is this clear? Any questions with regards to the architecture? So the parts like the IO embed, the edit decoder, and the program encoder, all of these there have been prior works done on it, and they are just going to use the same architecture for those. So they never really dive into all of this. They just mention what models were used for them. Yeah, so the models that were used for them are as follows.
Will you please go back to
sure.
here? So what do you didn't message on this line?
Sorry?
This line. S.
Yeah.
S is
is the start. It's the
just
start
an arbitrary start of the program. And here edit encoder. And why there's a line between two edit encoder here?
I believe that, okay, so based on the edits that has been done, because then you will make the next edit. So it
means that they're actually the encoder share the same weights.
Share the same weights.
Yeah, so basically the so-called edit operation. So if we want to make an edit, it's not just simple an edit function or instance. So basically an editing. So all of us use Git, right?
Yes.
So when we talk about the concept of commit, it usually means a version previous version, a current version, and a change between VP and VC, right?
Yes.
And all these three components consist of a commit. And a commit is basically an edit, right? So when we're talking about edit operation, we usually talk about what a program before the editing and what a program after editing, and where do we need to apply the editing on the original program, right? So I think that is kind of complicated stuff here, right? I can get a general picture. So overall, we are applying and generating editings, apply the editings, and generate editing again, and apply editing again. Right, keep going on, and finally we got a final version here.
Correct.
And before the so-called editing decoder actually takes the input of the set of input here, and the execution trace here, and
the program itself,
and the so-called program is here, right?
Correct.
And I think it's better. It would be very helpful if we can go into. Does their code be open source?
It's not open source. I can't find their code online.
Okay.
So
I'm very interested in how the trace will be used here, and how the trace will definitely be used for, and how the trace will be embedding. Because think about it, when we have a trace, the trace is actually a sequence of instruction executed, right?
Correct.
And when we executing the instructions, the program state will be changed.
Yes.
So where these program states will be part of the embeddings. And so I do have a lot of questions going on. If I can keep asking questions, I can ask a lot of questions.
Yeah, to be fair, I asked the same question because they didn't specify how their execution trace is stored. So the way I look at it, the execution trace can be stored in multiple forms. Like it can be the action that the robot takes, or it can be the entire grid as the trace itself. I feel that depending on how the execution trace is stored, it actually will affect the trace embedding portion that they bring up later. So in their paper itself, they actually never mention how the execution trace is stored. But what happens is that I went to look at another paper that they cited, and it's that paper also talks about some form of debugging. So that paper actually it's done, if I'm not wrong, that paper it's done without this part. So we can see of it as it embeds the input and output, and then it encodes the program, and then it passes it into the
and also I'm kind of interested about how the loss function or optimization function is defined. Right. So maybe we can count the number of parsing test cases, or we need to look into some internal states to be more specific.
Actually, for them, their loss, how it works is that they just take the proportion of correct. So it's based on proportion of correct test cases. So actually, they do something like I'm jumping forward a bit. But what they do is they did a best first search, and then based on the proportion of number of test cases that are the best, if all my test cases pass, then that's a valid candidate. If not, they will debug it, and then they will add it into the set, and then they will just keep trying to find the
So maybe let's go through the technical details one by one.
I'll go through it till we get there. So these are the models used. I feel it's not very relevant in this presentation. It's just designed based on the past research itself.
Also, basically, there are the so-called program encoders. It's just turn the programs into a vector, right?
Correct.
And it also basically the trace embedders and the IO embedders just vectorize all the inputs.
Yes.
But
the trace embedder. The trace embedder, it vectorizes the input, output, and the traces itself. Yeah, and then it concatenates them together. Yeah.
Okay, let's keep going on.
Okay, can.
So because it does not include the technical details, let's keep going on. Yeah.
Yeah, okay. So in terms of edit operations, which was the one that we mentioned just now, there are 4 edit operations. So I can keep the current program instruction. I can delete the current program instruction. I can replace the current program instruction, and I can insert a new program instruction. So for the
okay. So the so-called token is basically an instruction in this programming,
the
right?
token is an instruction. Yeah. So if we go back to here, so yeah, actually the edit operations itself, it's just a simple thing of whether it keeps or insert or delete with respect to this program token itself. So for the first 3, which is keep, delete, and replace, it stays at it moves to the next token. But if I insert, it actually stays at the current token itself, because I might insert multiple lines. So if we head back to this slide here, notice that when I insert a move function, it still remains. So assuming I have okay, let's look at it as I have a pointer. So let's say currently I'm pointing at this instruction. And then if it's keep, I'll move to the next instruction. Because it's insert, I'm staying at this instruction. Insert, I'll stay at this instruction. And then after that, when I keep, I'll move to the next instruction. So the idea is that if we go back to the diagram over here, so I guess the program token itself doesn't move. So if it's a insert instruction, the program token stays. But if it's any of the other operation, it moves to the next program token itself.
By the way, I don't think any operations will let it move forward, right?
Sorry?
Any addition operations, when we generate an arbitrary addition operations, and the program will be changed.
Yes, so I believe that this thing over here, the brown color line, it's just storing the edit operations itself. Then maybe after that, then they will go through the program itself to edit the program.
Okay.
Yeah, okay. So that's it. So the total number of edit operations is 2 and the size of the vocabulary plus 2. I think we are short of time, so I wouldn't ask the question. The reason why is the size of the vocabulary itself. So in this case, the size of the vocabulary is 4. It's because for the replace instruction and the insert instruction, it can take in any of the 4 instructions. So maybe I'll replace this current instruction with a move operation, or I can replace it with a turn left operation. And same for insert. So in total, actually there are 10 possible edit operations. Yeah. And this is also the part where I say it's not very practical, because if the vocabulary increases, the number of edit operations also increases quite a fair bit. Yeah. So yeah, so that is just something I think worth mentioning. Okay. Then so now down to the nitty-gritty details of the trace embedder. So the idea behind it was actually motivated by the breakpoints in IDE itself, where it actually keeps tracks of the execution trace. So they just want to embed the execution trace with the input itself. So the idea is that, let's say now I already have a so let's say right now I have a model. So my synthesizer has already created a model. So I would run this model that is created by the synthesizer on each of the input grids that I have. So if you recall the input grid, the specification can be written like that. So I would have a k number of input grids. So I will execute each of the input program on each of these k input grids. Then from there, I would obtain the execution trace for each of these grids. And after that, I would do an embedding. So the embedding is that I take the execution trace, along concatenate with the vector of the input and the vector of the output. Yeah. So this paper actually didn't mention the execution trace, how they are storing it. And actually, I think this is a very important factor, like how the execution trace is being stored. But another paper mentioned that it can just be the actions taken by the robot. So moving forward or turning left, that kind of thing. Yeah, so maybe in our case is that EK0 will be move, put marker. So that will be execution trace, so to speak. Yeah. So after they generate this so-called embedded form of the execution trace and the input and output, then what they will do is they actually create a mapping, a bipartite graph. So this graph is simple, is that it takes in the set of K and T, where K is the program itself, the grid itself, and T is the trace. So it does a mapping of the trace and the grid to the program token indices, which is I guess is what we would call the program lines itself. So we can consider that in our case is that line 1, 2, 3 will map to maybe move, and stuff like that. So line 1 would map to move forward, line 2 would map to move forward, and line 3 will move to map forward.
Oh, by the way, so
sorry,
sorry. So I need to raise a question. So given a bipartite graph, so this G is
the K and T.
K and T. T is the trace embeddings.
Yes, the trace embedding.
And K is
the grid.
The input.
The input grid, yes, correct.
Okay. Anyway, the input grid is anyway input. So and how this, since it is graph, how this is look, and is there a structure between the input and so if I understand that K1 T1 and a K2 T2.
No, actually it's more this is a pair. So it's KT. K1
T1.
Yeah,
and
K1
K2 T2, etc.
Yeah.
Right. And the other part is
the program lines.
Lines. Okay,
so based on the candidate program itself.
Okay, so maybe this is instruction 1, instruction 2.
Correct.
And instruction 1, and they will have a bipartite graph here.
Yes, correct. And
try to match their.
Yeah. So
and there's a mapping is one-on-one or minute.
Okay, so we'll look at the mapping over here, the second point. So the mapping exists if and only if either the instruction was executed to produce this state itself, or the instruction is a loop or condition where its body produces the state itself. So it's not a 1-to-1. In fact, it can be a many-to-1, because
but based on but anyway, so this graph is this part is not a ground truth graph, right? It is actually a graph.
It's not the ground truth graph. It's
the
candidate program. Yes,
it's the candidate program.
Yeah.
And based on, so consider this. So the program started from nothing, and we gradually synthesize it. And based on this instruction set, it cannot be generated loop and condition, right? How can it generate a loop condition?
I think it can generate conditional. The synthesizer can generate conditional.
Oh, really?
So
how could it? But anyway, so it will have editing operation, and based on your introduced editing operation, they just insert, delete, right?
Okay, yeah, correct. So, recall that the synthesizer is the one that creates the candidate program.
Yes.
Correct. So
and under what process can the synthesizer generate a loop of conditions? Right, according to your vocabulary, you only generate an instruction in the vocabulary.
This vocabulary that I have, this is only for the debugger. It's not for the synthesizer.
Okay.
Yeah,
So
the-
the synthesizer is still a black box.
Yeah, synthesizer is a black box
Okay,
to
okay,
us
okay.
because yeah, they are not focused on the synthesizer itself. They are just using existing synthesizers.
Okay.
Yeah. So
Okay. So basically, it's just telling us that whether this instruction is covered by this trace. If I understand it correctly.
It's just telling us that this instruction generates this trace. Yeah, pretty much it's that.
Or be covered by this trace.
Covered by the trace. I think it's more of the instruction is executed to produce. So let's say now I take a move forward and let's say my instruction is move.
Yeah, I think they're the equivalent. I think they're kind of equivalent, right?
Yeah, and the robot move.
No, the point is that if there's if condition, but the conditional value turns out to be false, it will not be mapped to the other trace.
Yes, correct. So that's why I feel it's very important for them to explain the execution trace, what's included in the execution trace, because this execution trace will also determine whether the if condition passes or fails.
Okay. So assuming that we have a bipartite graph, and we will have a mapping, and why it is have a why? So we do not need to calculate the optimized matching here, right?
Sorry.
Do we still calculate the matching? Matching means that we need to link together about the mapping.
I'm not too clear. What do you mean by?
So once we talk about a bipartite graph, we usually have the V1, V2, V3, and here is maybe W1, W2, right? So for a theoretical point of view of bipartite matchings, we usually the matching could be any pair actually any pair of the nodes. And for the bipartite matching, we usually find the maximal matching. Maybe this is 0.9 and this is 0.08. And the rest are all 0.1. So we pick up the matching here. Right. So this is a standard formulation of the bipartite graph.
Yeah.
And here they do not calculate anything. They just take the concept of the bipartite matching. So they're saying that so basically it's not a bipartite matching. I feel that.
Yeah, it's not a bipartite matching. It's just a bipartite graph, so that it helps them to do this part. I believe it's just to help them in this portion here where they are just trying to compute the vector representation of the related execution state. So what happened is this part here is actually, let's say I have a line. So something like what you have here, instruction 1 is linked to 2 different execution trace. Then I'm just taking the average of the vectors of these 2 execution trace.
Oh, so you mean that you try to embed the each line as the average of the embeddings.
Yes, correct. So based on the embedding, that's why I think the bipartite graph is only useful for them to calculate this embedding. After which this graph.
Okay, whatever it is, we have encodings of the instruction. And once we have instructions, we have so each program will be converted into a sequence of instruction, right? So a sequence of vector, right? Each program.
Yeah, the sequence of vectors is the instructions, right?
Yeah.
Yes, correct. So in this case, this portion here, this is okay. If you don't mind, I head back a few slides.
Okay.
So this is actually referring to this part over here. So it only consists of the input, output, and the trace. So they make use of the input, the output, and the execution trace itself, and they so-called concatenate them together to form a new vector. Then this vector will then be passed along with the program instruction.
But the embedding of the program instruction is calculated based on the embedding of trace. Am I right?
Sorry?
Well, based on the bipartite graph, the embedding of instruction or the embedding of the program can be calculated from the embedding of the trace. Because you can see this QI, right? This QI can be calculated based on the embedding of trace.
Yes.
So there's no need to represent the programs as, there's no need for additional embedding of the program.
Yes, that's why there's no program embedded, but when you pass it on, you will still need to concatenate the program. If not,
Okay, I understand. Okay,
yeah,
I got it. Okay.
yeah, correct. So the part that we were looking at is just here. Right. So after that, it will be embedded. So what is being passed to this edit decoder over here is this EPI prime, where it's a concatenation of the QI, which is what we described, as well as the original program encoding, which is this part. So yeah, it's just referring to this part over here. This concatenation is the concatenation of these two. Yeah. So I think the key point is that they actually included the execution trace into the program for it to be trained with. Yeah, that is the selling point, the so-called selling point of this paper. Yeah. Okay, so down to the training itself, they actually, so actually that's it for this trace embedding part. I know it's not very clear, but that's how the paper described this part. Yeah, so personally, I'm also a bit confused, especially with regards to like what is included in this trace itself. Any questions?
Let's keep going on.
Okay.
So,
okay.
Okay. By the way, is there any question for this part? I think it is. We can have a big picture. I still have some concern for the methodological design, but let's keep going on.
Okay,
but they do have some idea which is inspiring, because in your FYP project, we still need to embed a trace.
Yes.
Right. In the future, basically we need to embed the trace steps, but it is still an open question whether we need to use neural network model embedded, or we can use a very straightforward the feature engineering to do this. It is still an open question, but we're really interested on this part.
Yes, correct. Yeah, I was interested to find out how they embed their traces as well, like whether it's the whole state or it's just the action. Yeah. Okay, so in general, this part is just their implementation portion. So how they train their debugger is they actually took a two-stage training process. So instead of training on the synthesizer itself, they actually created their own program mutations. So the reason behind that is because a very good synthesizer would not make any mistake, or would make very little mistakes. And if you have very little mistakes to pass into here, your debugger cannot actually train. So what they do is...
So here, what is the target of the pre-training? And what is the purpose of pre-training? And what is the pre-training task?
The pre-training part of the debugger is just to learn how to repair the program. Yes, so
okay. So when we talk about the pre-training, usually we pre-train for a better representation. This is the idea for a lot of the neural network model or machine learning tasks. And here, what is the goal of the pre-training? So, and maybe I write down here. So the debugger is going to try to
repair the program.
Okay, so maybe it's more like a repairer, right?
Yes, it's the repairing part.
It is actually the repairer. The repairer is going to generate the edit operation, right? And so this is a goal. And if we want to generate edit operations, basically we still need an embedding, right?
The embedding of the
program. Embedding of the program here.
Correct.
So here we are talking about the so we still talk about the embedding or presentation of the program. And okay, so the next one is that what is the pre-training task?
Okay.
What is pre-training task? So you're talking about the pre-training, and just like the word embedding. So here we're talking about the program embedding, right? Given a piece of program, we try to embed it so that the neural model can generate its edit operation. So, but how do we embed the programs, and what kind of task are we using to train the program
Okay,
embedding.
yeah, can. Okay, so the embedding itself, I believe it's done using the program encoder itself. So it's the same thing. Individual instructions are embedded. So the idea is now I just first to create this kind of mutated programs. So I have a ground truth program. So I have a P, and from P itself, I can actually maybe mutate certain lines of P to get multiple P primes. And then from there, that is the embedding. So the embedding is still the program instructions itself.
And here we are trying to improve the embedding, right? Improve the embedding.
Improve the embedding as well as the edit decoder.
Or may not improve the embedding. So giving you explanations, the embedding has already been used by the embedding of the instruction.
Right.
So in this case, we're trying to have a model
that is trying to improve the edit decoder to come up with a more correct edit sequences such that P prime can get to P. Yeah, so
when we train during the pre-training task, do we still need to feed the trace, the input output and trace, right? Okay, I got it. So here it's more like a data augmentation task.
I believe that this,
right? It's more like data augmentation, but the data augmentation is connected by the program mutation here.
Sorry, can you say that again?
The data augmentation. It's a data augmentation. So it means that for example, if we want to train the computer vision model or image classification, we usually need to sometimes the training sample is not large enough.
Yes, correct.
They artificially created some images like to add some Gaussian noise, and we brighten the image a little bit. We switch and flip it a little bit. It's all called data augmentation.
Yeah.
And now the training samples is program code, and since the program code is not just enough, so in order to enlarge the training data set, they do the data augmentation based on the program mutation in this case.
Yes, correct. Okay. Yeah. So that's essentially the pre-training portion, and then after that they fine-tune it with the actual program synthesizer. So the programs that are generated from the synthesizer. So that's the fine-tuning portion of it. Okay. Yeah. So
it means that the edit sequences need to be defined in advance.
No,
not sequence. Edit
operation.
Yeah.
So there's only 2V times 2 operations. Plus 2. Operation there. So it's more like a vocabulary. But for each instructions, there is supposed to be this number of the edit operation, right?
Correct. Yeah, it can take any of these edit operations.
Okay.
Yeah. Okay.
And I think this methodology is kind of complicated, and there's a lot of important information missing here. Okay.
Yeah.
But we can have a general picture here.
Okay. Yeah. So after that, then for the inference procedure where they determine which algorithm or which candidate program to use, they actually use a best first search. So I think I will dive into the best first search algorithm first. It's quite wordy, but the main parts are my comment. The blue one are my comment. So this best first search, what it does is that first it takes in all the examples. So this actually is their entire algorithm. Yeah. So it takes in all the IO examples that we have, the IO example pair. Then based on the synthesizer itself, it generates out all candidate programs. So this is actually your frontier for the best first search. And then this is the S is all the already explored candidates, which we don't want to explore further. So at the start, it's an empty set. Then for I in range, so we can choose to do this operation for X number of iterations. So if we are able to get a successful candidate before that, we will end this iteration. But if not, maybe, so I think for their case, they actually did 100 iterations of this. So what happened is they actually execute the program. So whichever program that is created from here, from F, for every program in F, they actually executed it on all the examples. And they test to see how many of it satisfy the examples. So let's say I have 10 examples and I have 3 programs. Some of them, maybe it can only get 10%. Some of them maybe 80%. So after that, it max of it to take the best performing, best performing program. Then if the best performing program itself already achieve 100%, then that is the successful and valid program. So it will just return it. If not, what it will do is it will debug the best performing program with all the examples that we have. And then this debugging actually creates more candidate programs for us. And these programs will be added into F, the frontier itself. And then when we run through the loop the next time, it will be determined based on here. Yeah, so for example, it's possible that the debugger might create candidates that are worse than the existing set. So it might create, so let's say right now I have 3 different programs. One is 10%, one is maybe 50% success rate, and one of them is 80% success rate. So by right, the algorithm will choose the 80% one, and it will pass through the debugger. But the debugger might cause it to drop, might produce another 2 programs, one of them with 25% and one of them with 40%. So we know that, so in the next iteration, we will actually take the 50% algorithm as the best candidate instead. Yeah. So the idea is that, let's say I hit a dead end, right? I would turn around and I will go and take the next most promising candidate. Yeah. So that's why it's a best first search. They tried best first search and greedy search. Best first search performed better. So ultimately they use best first search. Yeah. Then if after the 100 iterations it's still not able to find a valid successful candidate, then it will return a argmax of all the possible frontiers, all the possible programs in the frontier. So for our case here,
So
for our case here, it might return 80, the 80%, even though it has been explored, but it's the best performing algorithm, so it's the one that's returned. But if it gets to this line over here, this program is likely a failure program, unless the last step here actually resulted in a valid program to be generated.
Okay, that's quite straightforward. Okay.
Yeah, it's a very straightforward algorithm. So the idea is that this is just an infinite tree. So there's an infinite number of candidates that can be generated, and every node is the program itself and its children, which is generated by the debugger. So yeah, we can see how it works. So
the contribution here is just like the debugger. Right, so it's more like I think it's not correct to say it's a debugger. It's basically a repairer.
Yes, a repairer.
Right, because it does not dive into the root cause why the program failed. It's just trying to synthesize or repair a buggy synthesized program to see whether it can be fixed to pass all the test cases.
Yeah. Correct. Yeah. Okay. Yeah. So the main contribution is the repairer, which is something that a lot of the other prior works don't have. Yeah. So in terms of the experiment, they use the Carrel benchmark, which is the same thing. It's a grid, and then with the input and output. So for each sample in this benchmark, there is a ground truth program, which is the P star. And then I have 5 input-output pairs as the specification and 1 input-output pair for a test. So this is the hidden test case. 3 is the hidden test case to make sure that nothing like the if-else statement program will pass through. Yeah. So
there's so large number of programs
Correct.
for just the carrier benchmark.
as in, I believe that's the reason why for program synthesis people will use this benchmark, because there's a lot of ready samples and
and this is actually a very, very simplified program, right?
Yes, correct.
And even for such a simplified programs, if they want to achieve good results, they go with 1 million training samples for synthesizer program.
Yes.
And these programs are randomly generated program, right?
Randomly.
Right. Otherwise, how could you find 1 million programs?
I don't think it's randomly, because if it's randomly means that it was synthesized.
Yes. Yeah. Of course, it could be randomized. Otherwise, how could you find 1 million carrier and a carrier? If you tell me that it is 1 million Java program, I will believe it. We'll say that you have 1 million carrier programs, and who are going to run 1 million?
I think if it to generate this, idea maybe.
I think we can randomly randomly generate an arbitrary programs. And once we generate the programs, we can take the ground truths, then create the input and output. And after that, we can synthesize the originally generated programs based on this input and output.
Okay.
So maybe that is a way to do this. But here, I still have the concern. The reason is that once we generate such a program, okay, maybe it's okay that once we randomly generate a program, that this program per se actually is a specification, or that's just a specification. And the problem is that whether 5 pair of input output is enough, right? So suppose we have a very complicated programs, and a 5 pair is just a partial specification. So I have a concern. If I'm going to do this, I'm going to at least generate 1,000 input 5, but it may challenge the model scalability, right? Otherwise, I think 5 pair of input and output is not enough to specify the specification.
I guess
you can think about it. Let me have a metaphor here.
Yeah.
Suppose I have a program P here. And if we're using P to derive 5 pair of input and output, these 5 input output is just an estimation of the specification mentioned in P, right?
Yes.
But let's take another machine learning perspective. Suppose we have 5K images, saying that this kind of images is actually dog. Okay. So the reason we're using 5K images to specify their dog, because we cannot have a very clear definition of what images can be a dog, right? But now we have very clear specification the program looks like, and why we generate only 5 input output. And 5 input output, is that enough for the machine to learn the real specification? So here is my concern here.
But even if it's too little, since we have the ground truth program, we can actually run the ground truth to generate more specification.
I agree. But just here, this
sample might be too small.
Okay, let's keep going on.
Okay, yeah. So overall, so there are a few things. So as I mentioned just now, there is the generalization metric as well as the exact match metric. So generalization is that so long as it passes all 6 input-output tests, so the 5 specification and the 1 hidden test case, then if it does passes all, then it is generalized. And this is actually the focus of it. Because exact match is quite hard to achieve, because like it must be a perfect match with the
exact match means from the program instruction level it will be exact match. But the generalization means that we just as long as
input and output are the same. Yeah, so actually their focus is on the generalization. So this table over here is actually showing their results. So as we mentioned, the synthesizer can be any arbitrary state-of-the-art synthesizer. So they actually use a few synthesizers over here. These three are all different synthesizers. Yeah, and if we use only the synthesizer, so over here, the value outside of the bracket, that means all of these values, they are the generalization error. So lower is better, cause lower error. And those in the bracket are the exact match error, which is not very important to us. So yeah, we will just look at the generalization error. Yeah, and it's able to perform. So the synthesizer on its own, it performs quite badly. But once we add in this kind of debug repair work, so okay, let's go through the four
Here
different.
I have a question here. So how, because the model or debugger didn't see the generalized sample or the test sample, right? They can only look in the training sample. So it means that the debugger or the repairers can only improve the training accuracy instead of the testing accuracy. Think about it.
Yes,
so
correct.
So we have some training set here,
Mm.
and we have some testing set here. Right?
Yes.
And the testing set is going to decide how generalized, about generalizability. And the training set here is going to about the training accuracy. Here. So based on their methodology design, they can only improve here instead of here, right?
So, but assuming there's no overfitting, if we improve the training accuracy, won't the testing accuracy also increase?
No, you're right. But they just showing the test accuracy, not the training accuracy here.
Yes. Sorry. So yeah, this is just the.
This is a generalization
accuracy
error, right?
And
so
yeah,
and there's no difference between whether we're using tracing value or not, right? There's not much difference.
Not much of a difference, actually. Yes, that's why.
So it means that tracing value does not provide any information there.
It does not provide much information.
Yes, by the way, so since the program embedding is just based on the tracing value, and if there's no tracing values, how could they derive the program embedding?
No. So if there is no trace embedding, sorry, I'll go back a few slides. So if there's no trace embedding, means that there isn't this portion over here.
Yes.
So it goes from the program encoder directly to the edit decoder.
Yeah, so the programming, but here you can see this QI is derived from EPI, right?
Oh yes, correct. So when they are running it without the trace embedding, they do not have QI.
So
QI comes from.
So they're using something else to replace
yes,
QI.
Correct. So it's just EPI. Yes.
Okay.
Correct.
So
yeah.
my argument here on this slide here is that the debugger or repairer actually cannot improve the testing accuracy or generalizability. Yeah, and I think they just switch the concept saying that their approach can improve the generalizability, but basically they only improve the training accuracy. So that is the basic idea. And as for the generalizability, it's just a byproduct caused by their improving of the training accuracy. Okay.
Yeah. So that's pretty much it. Then the other experiment that they did was the program repair evaluation, which is actually the trace embedding. So before they included it with the synthesizer, they also did just on the program repair itself. So just with the trace embedding. Okay, so if we recall over here, yes, so if we recall the training phase itself, there's actually a two-stage training. the pre-trained part where they train on the mutations of the programs. Yeah, so actually when they tried their programs, the mutations on their trace, whether on a model with trace embedding and a model without trace embedding, these are the results. So okay, maybe I explain slightly how this data set comes about. So if we recall the pre-training step, we have a ground truth program P star. And then from P star, we actually create mutations to see how well, so that we have more. So we did data augmentation so that we have a lot more data. So maybe from P star, I can create P1, which has 1 mutation, P2, which has 2 mutations, and stuff like that. Okay, so the idea is that this graph actually, okay, if we just look at the generalization error portions here, we can see that based on the graph, actually with the trace embedding on mutated programs, it actually performed better, slightly better. Yes, but this is only on mutated programs. But
not necessarily. What do you mean? This is 1, 2, 3, 4,
yeah.
5.
So how many?
This is manual imputation. But what does these 3 and 5 means?
Okay. Yeah. Okay. So these 3 and 5, right? So they actually train 4 different models. The first model that they train is without trace embedding on programs that have 3 mutations. And here they train one that has no trace embedding on 5 mutations. Then this is with trace embedding on 3 mutations. So all the data sets that they have is with 3 mutations only. The training data has 3 mutations. And this one, the training data has 5 mutations. So we can see that for if we are looking at, like, let's say the number of mutations, right? If we look at the one with 5 mutation, the one that was trained on 5 mutation performs the best, which makes sense. But actually we can see that the one, if we focus on this blue part here, we can see that the one with trace embedding that was trained on 3 mutation performs worse than the one that has no trace embedding on 3 mutations.
So here the observation is that
there's overfitting, severe overfitting.
What is the difference between the first and the second picture?
Sorry, which one?
What's the difference between? Oh, this exact error. So
this exact error, and this is generalization error.
So here the conclusion is that the trace embedding can play a role when the number of mutations increase.
Yes, correct. But but it also shows that actually there's quite a bit of overfitting in their algorithm. So actually, the moment there is more than the amount that it was trained on, it starts to perform worse than the one without trace embedding. Yes. So that is something that they mentioned. It overfits due to its larger model size.
Okay.
So all in all, actually, personally, my takeaway is that it's good in theory, but actually it's not really improving by much. As if we look at it over here, the one with trace embedding and the one without trace embedding, there's actually very little difference between the two. So there isn't really a need for that. Yeah. I feel that all in all, like
I think my gut feeling is that this approach is it's kind of system. So there are so many components which can decide its effectiveness.
Yes.
For example, whether the program embedding works well, whether the trace embedding works well, and whether the program repair, the pre-training can work well. And when combining all of those factors, we need to make sure. So if I'm the one, if I'm the reviewer, I would suggest that this paper go for a journal paper instead of conference paper. Maybe, yeah, because this paper is not self-contained. If we really want to follow this work, we definitely want a version which is more self-contained, can very specific on what is program embedding and what is trace embedding, and there are so many, just like Yufan's talk, right? There's so many people. Here it is still open question to embed a JavaScript or Java or Python programs. Very complicated. It's open questions. We know that the carrier programming languages is kind of simple, but for such a simple program, and how to embed it, and what is the supposed programming encoder, and also is largely. So anyway, you can see from the experiment that the trace embedding, at least from this table, the trace embedding doesn't play any role here.
Yes.
Right. So
Yes.
it's hardly to see any difference between the trace, and that means the trace embedding is not that successful, and the neural network model ignore this information. So anyway, that is providing an interesting point that it looks at the embedding and the using mutation to generate repair. But yeah, but there's so many open questions. And for the approach, and I suggest that you try to investigate what is the trace embedding. And my gut feeling is that this trace embedding is heuristic, simple, and impractical. That is my gut feelings. And when you look at these embeddings, and I think we need a discussion on what is more practical embeddings and what's supposed to be. And I have two thoughts on this part. The first is that you can think about the trace is actually a sequence of the program statement, right? So suppose, or a sequence of instructions. So suppose this instruction is add, and the second instruction is subtract. The third instruction is call function. So, but anyway, the actual program has a loop and if else relations. And how do we, and this sequence basically is a traverse on the program dependency graph. And how do we encode this kind of information, and whether this information can be made more concise? You can think about it when I'm talking about program execution, it can be very, very large, or its length can be very, very large. And definitely it cannot fit into the state-of neural network model. And whether they have some concise information to represent the trace, right? So this is from the first perspective. The second is that we can consider the state machine. And if it turns a state machines, and what is the precondition and post-condition, and what is the side effect for each steps? Maybe that is also a very important information for us to embed the trace. So maybe we can think from these two directions and to propose our own trace embedding technique.
Okay. Yes.
And also, I suggest that you look into the trial. Anyway, so theory is theory, and usually there's a very classical statement or claim that the talk is cheap, showing the code. So when we go through so many papers, understand the theory, and it really matters whether we can make this theory be practical. And whether we can really automate a lot of engineering, automate a lot of programming tasks. So that is very important. So I suggest that you spend a few time, and I know that you're quite busy with your internship, but you spend some time to understand how the progression looks like. And when you get confused, I think I appreciate Darren a lot, because he keeps raising questions and let me know that whether on the, for example, the framework or ESEC, that's a documentation. Maybe it's not the problem of not problem of student, but the problem of the framework and the project itself. So we can increase the understandability or improve the documentation of the project. So that is also very important. But it needs your investment. It need you to spend some time on and try to understand the project.
Okay. Yeah.
Okay. Please.
That's it for my presentation. As in, I'll be done with my internship in 2 weeks. So after that, I think I'll have a lot more time to spend on this. Yeah.
Okay, and also the regression is highly dependent on the microbat project. So you can discuss with Chen, and we can have a further discussion. Okay. I assume that everyone here became a bit tired. Let's call it a day. And thanks very much. It's really a fairly long discussion. And thanks everyone. Bye.